These two particular topics are a bit different from what we have discussed so far, and one of the topics seems to be very difficult. Hello students, this is your friend Sumit, and today we are going to discuss topic 12 of this series, that is alternating current and electromagnetic waves. Alternating current is the chapter from which many of the student fears, but trust me, it is very easy to score in this topic. Why so? Because there are hardly any varieties. Just you understand few of the key concepts, just practice those varieties, very easily you can solve the questions. And I'll show you very easy methods to solve the question. You can solve the AC circuits just like a DC circuit, just by understanding the things that I'm going to discuss. Okay, with that we are having electromagnetic waves. This is one of the smallest chapter, and it is having a good weightage also. So these two topics, if you ask what is the weightage, we can expect up to 2 to 3 questions from them. And AC, very easy to score. EM waves, which is very small, having good weightage, it means a very good opportunity to score. Okay, so with that I'll be giving you a good set of hand-picked set of questions for practice also, and that you can access from the link that is given in the description. When you click that link, you'll go to the PWF, which is the most trusted educational platform and trusted by many of the top rankers, and you can access the notes of this video as well as the DPPs there to practice. Okay, so let us begin the discussion. We'll be covering 2 chapters today. First is the alternating current and second is the electromagnetic waves. We'll be covering entire thing, all the subtopics that are required for JEE Mains. Now if you ask me what are the most important topics among these two chapters, I'll say from alternating current, so you should at least, if you can understand all the concepts, that is great, well and good. But if you have some time limitation, let us take, so at least understand series LCR circuits. Okay, how to find the current there, how to find the impedance there, how to write power, okay, dissipated in the circuit, all those things for series LCR circuit. Okay, and some fundamentals of alternating current, the RMS value, how we find, the average value, how we find, all these things. So these are the things which are more frequently asked, I'll say. From electromagnetic waves, now how to find the corresponding magnetic field component of electromagnetic wave. Okay, so we have electric field given and how to write the magnetic field, the intensity thing, the energy density, and how to write the speed, how to write the wavelength, all those things. And also the application part is also very much asked, like many times in tabular form. In one side some applications will be there, and other side the name of the corresponding electromagnetic waves will be there. So now there you need to match it. So that type of question is also very much asked from electromagnetic wave. Okay, so now let us begin our discussion with the first topic, that is alternating EMF or alternating current. So what is basically alternating current means? Alternating means it is alternating once towards the positive side, then towards the negative side. Okay, so if I draw the waveforms for alternating current, let us take axis. Okay, now alternating current can be triangular in shape, it can be like this. These are alternating triangular waves like this. So it is positive, then it is negative, so it is alternating. It is you can say here the magnitude is varying, at the same time the direction is also varying. Here if I see, it is towards the positive side, okay, then it is towards the negative side or in the negative direction. So I versus T. Similarly for EMF also, let us take, it may be EMF also, E maybe for alternating EMF. Now this is triangular, it can be square shape also. How? It can be like this as well, square shape. Okay, somewhat like this. It can be of sinusoidal type also, like let us take this color. So it can be of this type also. These are all alternating. Now mainly when we will be talking about, the sinusoidal waves. Sinusoidal means it will be a function of sine or it will be a function of cosine. So for current, if I say, let us take somewhat like I naught sine of omega t plus phi. Okay, so this is our sinusoidal current. Here this is the amplitude of the current or the maximum value of the current, okay, and omega t plus phi. If you see when time is changing, okay, sine omega t plus phi will oscillate, okay, so my current will be oscillate, or I'll say it will be of alternating nature, okay. Similarly, I can have my EMF also of similar type. Let us denote it with V. So it is somewhat like V naught sine of omega t plus theta. So this is my alternating EMF. So sinusoidal, it can be function of cos also. Here I am writing a sine function of sine. Getting it? Okay. Now let us talk about average value of alternating EMF. How to find average value of anything? Anything. So you know, when I'm talking about sinusoidal, let us take sinusoidal only, okay. So it will be having some time period, it is repeating itself in that particular time period, okay. So here if we see in the previous slide, here I will say, let us take, this is when omega t is equals to pi, this is when omega t is equals to 2 pi. So when omega t is equals to 2 pi, it is repeating itself. So if I ask you the time period, you will say that is 2 pi by omega. So it is repeating itself after a certain time period. Now if I have to find the average value, how will I find that? So I will say integration of, this is my I, integration of I dt from 0 to its time period divided by the time total. So this will become my I average. Getting it? So let us take my I is some function of sine. It is like I naught sine omega t. If you find the average of sine omega t is 0, because for half of the time period it is positive, for next half of the time period it is negative. So when you make the continuous sum or integration, the total will be 0 from 0 to 2 pi, isn't it? So I will say my I average will be 0. And similarly, if my sinusoidal EMF is there, I will integrate to find the average divided by the total time. So it will also come out to be 0. And from the graph also we can see, let us take, this is my current or voltage and this is my time. So when I am saying average, I will take over one time period. When you integrate it, whatever is the positive value here, the same negative values are here, okay. So total will come out to be 0. So I average is equals to 0. Now if I ask you find the average of half cycle, then it will not be 0, isn't it? Then it will not be 0. Here it is 0, because when I am talking about average, so by default we will say it is for complete cycle. But if I ask you find for average for half cycle, when you talk about half cycle, it's not 0, it's positive. So it will be non-zero there. We'll come to that. Now RMS value of alternating current. How to find the RMS value? So when I say RMS, what it is? R means root, M stands for mean, S stands for square. Okay, so let us take, I am having current like I is equals to I naught sine omega t. So what you do? First you square, okay, start from the right hand. First you square, then take the mean of that square term, then take the root of the whole. So first you square it. Square, if I square it, what it will become? I naught square sine square omega t. I squared it. Now take the mean. So I have to take in complete time period. So when I take means, I will say 0 to t dt divided by t, where t stands for the time period. So this becomes the mean of the square. Now root. Now take the root of this. And this becomes my IRMS. Now we need to solve this. How to solve this? I naught square is constant, take that out. Sine square omega t, sine square theta, I can write in terms of cos theta. Okay, how to write that? So you can write it as I naught square is constant, I'll take that out. So if you take that out of the root, it will become I naught. So out of the root I naught. Integrate, now we have square root, okay, so by t is there. So sine square theta I can write as 1 minus cos 2 theta by 2, okay. So this will be 1 minus cos of 2 theta. So 2 omega t by 2, yeah, by 2, and then here dt. Simple. Limit also, what is the limit? 0 to t. T is what? T is 2 pi by omega. Now 1 is constant, so when you integrate it from 0 to t, it will become t. Cos 2 omega t. So when you integrate cos 2 omega t from 0 to t, now I am integrating cos 2 omega t, okay, from 0 to t. T is what? 2 pi by omega, the time period. So here my theta is going from, if you see this 2 omega t, this will go from 0 to, when you put here t as 2 pi by omega, so what it will become? 4 pi. So from 0 to 4 pi, so there are 2 cycles, okay. So some will be 0 only, because whatever positive is there, negative will also be there. So this will come out to be 0. So this integration will give us 0, and this integration will give us t, that will be cancelled with this t, only 1 by 2 will remain. So this becomes I naught by root 2. This is my IRMS. What is I naught? I naught is the peak value of the current. So the RMS value is 1 by root 2 times of the peak value. It is 1 by root 2 times of the peak value. Getting it? Let us highlight it. It is very, very important to understand. Okay. Keep this thing in mind. Same way, if I write for RMS EMF also. So if I say ERMS or VRMS, anyways, let us write as ERMS or VRMS, because I will be using V. So let us write VRMS, that will be V naught by root 2. Is this point clear to you? Is this point clear to you? Okay. So keep this thing in mind whenever we say find the RMS value of this. Okay, let us take a sinusoidal function is there. So the peak value of that divided by root 2. So when we talk about VRMS, the peak value of that divided by root 2. If a single function is a single sinusoidal function is there, then you can write like this. Now there can be some variations in that. We'll come to that. We'll take a question on that also. Now let us find the mean value in half cycle. As I mentioned, in half cycle, if we talk about, the mean will not be 0. In full cycle, the mean is 0. Whatever positive is there, the negative is there, total sum will be 0. But in half cycle, the mean will not be 0. So let us take the current as like this. Okay. Now take the half cycle. Half cycle means like this. Okay. So this is, let us take my omega t. Okay. And this omega t goes from 0 to pi. This is the peak value, which is I naught. Now in half cycle, if I find average, so average finding formula will remain the same. What is that? Integration of I dt divided by integration of dt, which gives us t, and this 0 to t. Now here, when I write it, I will write it as integration of I naught sin omega t dt. Time goes from, omega t goes from 0 to pi, time goes from 0 to pi by omega. So time goes from 0 to pi by omega divided by here this t, and if we put t as pi by omega, so we can write it like this. Now integration of sin omega t is minus cos omega t divided by omega. So this will become I naught integration of sine theta is minus cos theta, so minus cos omega t divided by omega, here we are having pi by omega, okay, and the limit goes from 0 to pi by omega. So what it will become, omega is getting cancelled, I naught by pi, okay, a negative sign is there. Now cos omega t, when you put t as pi by omega, it will omega t will go from 0 to pi, so this integration will become, so when you put the limits here, it will become what, 2. So when you put cos pi, that is minus 1, okay, and when you put 0, that is cos 0 is 1. So this will become 2 I naught by omega. So what is average value for half cycle? That is 2 by pi times the peak value. Average, this is for half cycle. So what it is? 2 I naught by pi. And same way for EMF also I can write, if that is V naught, so it will become 2 V naught by pi. Okay, let us write that also. So V average for half cycle, so that is 2 V naught by pi. This highlighted. Keep this thing in mind. Now let us come to a question. Now here it is asking for RMS value of this current. Now if you only ask the RMS value of this, I will say RMS of this will be root 56 by root 2. Peak is root 56 divided by root 2. Now here we are having one more constant, that is 6. How it will change the value of RMS? Now when I say RMS, what I will do? I will write it first. 6 plus root of 56 sine of 100 pi t plus pi by 3. This is my current. Now first, when we say RMS, first square, then take the mean, then take the root. So square this term, square, then take the mean, integration of dt, okay, divided by t, my total time period, and my time will go from 0 to the time period of the complete cycle. Here my omega is 100 pi, okay, omega is 100 pi, so I will say my time will go from 0 to 2 pi by omega. Omega I am writing here as 100 pi. This is my, and root of this, that will become my IRMS, so I will say this is my IRMS square. Okay, now how to simplify this? So first you can open the square terms, okay, it will become 6 square plus a root of this whole square plus 2ab, a square plus b square plus 2ab, and then integration of dt. Now when you write it, so what when I'm saying is, when I'm opening this and writing everything, it is taking time, but I'm showing you the way, okay. Once you understand it, you can very quickly do this, okay. So when you will square it, it will become 6 square. 6 square is a constant. When you integrate that 6 square from 0 to, let us take this as t, 0 to t, it will become 6 square into t only. Getting it? Then root of 56 into sine of 100 pi t plus pi by 3. Okay, so I will say plus this root of 56 sine of 100 pi t plus pi by 3. Okay, this square, okay, this square into dt, integration 0 to t, plus 2ab. When you write that 2ab term, that will become 2 into 6 into root 56 into sine of this. When you integrate it for the complete cycle, integration of sine for the complete cycle will give us 0. So I'm just writing 0 there. Getting it? Divided by my t. So here what it will become? It will become 6 square plus, what is this? This is IRMS of this. That will become IRMS of this only, isn't it? Integration of this square from 0 to t divided by t, that will become the IRMS square of this. Okay, root is not there. So IRMS square of this. What is the IRMS of this? That is root 56. Root 56 divided by root 2. So that is root 28. So basically it will be root of 28 square, that will become 28. Okay, so that becomes my 28, and that's all. This is my IRMS square. So take the root, so it will give us IRMS as root of 36 plus 28. It is 36 plus 28. What it is? 364. Yeah. 4. Yeah. So that is 64. That comes out to be 8. Root of that is 8. So this comes out to be 8 ampere. So whenever such question is there, now first thing is, what is the RMS value of a constant? If a constant is there, if I ask you what is the RMS value of a constant, how will you find that? Put here constant 0 to t by t, that will become that constant only. So RMS value of a constant is constant only. Now when you are having a function like this, okay, first term, there may be some additional cost terms also, there may be some additional other sign terms also, and you have to find the RMS value. So how you do? IRMS is equal to, let me write it, where should I write? Let me write it here with a different color. So I'll say my IRMS is equal to root of I1 RMS square plus I2 RMS square plus I3 RMS square and so on. Whatever may be the terms, okay, number of terms, you can just continue taking the RMS square of them. So what is the RMS of 6? 6 only. So root of 6 square. What is the RMS of this term? That is root 56 by root 2. So root 28. Root 28 square is 28. Just do like this. So remember this formula, keep this formula in mind. So IRMS is root of I1 RMS square plus I2 RMS square plus I3 RMS square and so on. Another question. An alternating voltage that is given to us is applied to a purely resistive load. The time taken for the current. Okay. So first of all, let us do, I think this question is placed before the next topic. Yeah, this question should be after the next topic. That will come, I think. Yeah, that is there. Anyways, let us discuss about when a resistance is connected to a AC voltage source. So AC voltage source is there. This is an alternating EMF. How we will show this? We will show this like V0 sine of omega t. Let us take it like this. V0 sine of omega t, where V0 is my peak value, and if you ask me, sir, what is the RMS of this voltage, so I will say that will be V0 by root 2. Now, I need to find current as a function of time. Let us apply KVL by moving in the loop. We can apply KVL, isn't it? Yes, we can apply KVL in AC circuits also. Okay, it's not that we can apply KVL only in DC circuits. No, we can apply KVL in AC circuits also. So now move in the loop. Here my current is I. Okay, when I am going through this, first we will get E. So let us take at that instant, this is plus, this is minus. Okay, the direction of current is like this. Although this direction of current will keep on changing with time, but I am talking about a particular instant. At a particular instant, this terminal is positive, this is negative, and this is the direction of current at that instant. Now I move. So this is plus E, then it's a drop in the inductor, okay, in the direction of the current. So how much that will be? Minus L d, oh, not inductor, this is resistance R. This is a resistance, okay. So minus IR, drop in the resistance in the direction of current, okay, and this becomes equal to my 0. So I'll say my E is basically equal to E by R. My current I is E by R. What is E? Is V naught sine of omega t. So the current becomes like this. So current becomes I is equals to the maximum value of the current I naught into sine of omega t, like this. So I'll say here my peak value of the current I naught, what is that? That is V naught by R. Here if you see, when the current will reach maximum or when the voltage will reach maximum, the current will also reach maximum, because this is also function of sine, this is also function of sine. If I ask you what is the phase difference between the two, you'll say phase difference is 0, isn't it? What is its phase? Omega t only at a particular instant. What is the phase of this? Omega t only at a particular instant. So here the phase difference between voltage and current is 0. So I'll say that my current is in phase with the voltage, or vice versa also I can say my voltage is in phase with the current. So let us write that. So we'll say that the current is in phase with voltage. Or in different words, if I say the phase difference between voltage and current is 0, when only resistance is there. If inductor or capacitor is also there, then this phase difference will be there, it will not be 0. Okay, now let us draw the phasor. How we draw the phasors? You see here, my voltage is with the time, if I say it is changing with time, isn't it? At a particular instant I am writing this as V naught sine omega t. V naught is the peak value, okay, but at any particular instant it is changing as a function of sine. So I can represent this with a phasor diagram. This is for resistive, okay. It is a way of representation. Phasor diagram is a way of representation. Now, how will I represent this voltage? You see, this my voltage is V naught sine omega t. So V naught is the peak value. So I'll show a vector like this. We call this as my voltage phasor, and its length represent the magnitude. Okay, what is that? V naught, the maximum value. Let me take a proper arrow from here. It is like this. This length represent the maximum value, that is V naught, and it is rotating. This phasor is rotating like this in anti-clockwise direction with an angular velocity of omega. It is rotating with an angular velocity of omega. So at any particular instant, if I ask you how much is this angle, you will say this is omega t. Okay, it is rotating in anti-clockwise direction with angular velocity omega. At any particular instant, this angle will be omega t. And if you ask how much is the y component of this vector or this arrow, let us take the dotted line, means this length. How much is this? This is my V naught, this was V naught, okay. So horizontal is V naught cos omega t, vertical is V naught sin omega t. So this is my V naught sin omega t. So when we say phasor diagram is a way of representation, okay. Here we show our voltage or the currents like rotating vectors. Okay, so so this V naught is the magnitude of this. Okay, it is rotating in anti-clockwise direction, and at any particular instant, if you want to find how much is the value of the EMF there, you take the y component. Okay, so the component along y axis we are taking. You may take along x also. Okay, so then you may represent your omega in clockwise direction or like that, different way. But anyways, by the standard that we follow is we take the component along y axis. Okay, and we take this to be rotating in the anti-clockwise direction. So at any particular instant, if you ask me how much is the voltage, I'll take the y component. I'll say voltage is V naught sin omega t. Getting it? Now let us represent current also. Now what is current? My current is I naught sin omega t. Current is I naught sin omega t. It means the current is in phase with the voltage. Its angle will be omega t only, but the amplitude, okay, here is I naught, that is V naught by R. So amplitude will be different. So show it like a let us take another color like this color. Oh, it's a dotted one. Yeah. So this becomes my I naught. And if you take similarly its y component, it will become I naught sin omega t. So here we can see from these two vectors, they are pointing in the same direction, and by seeing this phasor diagram also I can say my V naught and I naught are in phase. If they will be out of phase, or let us take some angle between them, so then either I naught will be leading or I naught would be lagging. Is this clear? Okay. So in resistive circuits, if we talk about, the current and voltage are in phase. Therefore, we drew the phasor diagram like this. Now let us talk about the power. So what is power in DC circuits? So power, we say power is equals to V into I. This is how we write power. So if I write power for this, so I will say my power P instantaneous is equals to, at a particular instant I am writing the power dissipated. What is that? Whatever is the V instantaneous into I instantaneous at a particular instant, or I can write just simply as V into I. What is V? V is my V naught sin omega t. What is I? I is my I naught sin omega t. So my instantaneous power comes out to be V naught into I naught, okay, V naught into I naught into sin square omega t. At some instant the power can be maximum, at some instant the power can be 0. Now let us write the average power. Okay, take average both sides. So I'll say my P average will be V naught I naught is constant only into average of sin square omega t. So we already found average. Integrate sin square omega t from 0 to t in the complete cycle divided by the total time. And what is the average of sin square omega t? That is 1 by 2. So this will become V naught I naught by 2. This becomes V naught I naught by 2, and I can write this as VRMS into IRMS, isn't it? What is VRMS? VRMS is V naught by root 2. What is IRMS? I naught by root 2. So V naught by root 2, I naught by root 2 is V naught I naught by 2. So I can say this is VRMS into IRMS. So just like DC circuits, I can say the power dissipated is VI. Just like DC circuits, again I am repeating, I can just say that my power dissipated is just V into I. But here you have to take the RMS values, not the peak or instantaneous. Generally, when we say that find the power, by default in AC, that is the you can say the average power only by default. And when some current is mentioned or some voltage is mentioned, and in the question it is not mentioned that whether this is peak value of this or this is RMS value, then by default take this as RMS only. Okay, so when we talk in default way, I say let us take a 220 volt of AC voltage, alternating voltage is applied to a resistor. So now you will ask me, sir, this 220 is RMS or peak value? Default is RMS. So I will say that 220 is the RMS value. If I am not mentioning, if I specifically mention that I am applying a peak voltage, alternating voltage having the peak value of 220 volt, then it is the peak value. Otherwise, by default, it is RMS value only. So we got my power formula P as V into I, and that V and I represent the RMS values. So I can represent RMS value with capital letters. Okay, so V into I. I am representing the RMS values with capital letter. Whole throughout I will follow this same pattern. Okay, so here it means this is VRMS and this is IRMS. Now let us come to that particular question. Let us read it. An alternating voltage of 220 sine 100 pi t is applied to a purely resistive load of 50 ohm. The time taken for the current to rise from half of the peak value to the peak value. Okay. So if you write the current, so you'll say the current will be just V naught divided by R, that will become my I naught into sine of 100 pi t. Simple. This is my current and this becomes my peak value. So this is my I naught sine 100 pi t, or I can write this as omega t. If I ask you draw this curve, draw this current as a function of time, so it will go like this. Let us take this as my omega t. So this here omega t is pi. So he is saying it goes from half of the peak value to peak value. Half of the peak value means here when it is I naught by 2. So when it will be half of the peak value, when omega t is equals to pi by 3, because sine 30 is 1 by 2. So this is pi by 3, pi by 6, not 3, pi by 6. Sine 30 is 1 by 2. Okay, so when omega t will be my pi by 6 or 30 degree, it will be I naught by 2. Okay, I naught by 2. When it will be peak, when omega t is pi by 2. So here my omega t is pi by 2. Pi by 2. So how much is this angle? How much is this angle? This angle is pi by 2 minus pi by 6. That becomes pi by 3. So this is pi by 3. This is my total angle. Okay, the difference here. And with what rate this angle is changing? Omega. So this angle is my omega into delta t. I am taking this duration as my delta t. Okay, so delta t is pi by 3 omega. Okay, now again if I am writing, let us take here time is t1, here time is t2. I can write like this also. My omega t1 is equals to pi by 6, omega t2 is equals to pi by 3. Subtract these two. So this is omega t2 minus t1. This is omega t2 was pi by 2. This was pi by 2. Subtract these two. So this will become pi by 3. Okay, so this is how I am saying omega delta t is pi by 3. That way also I can say. So delta t becomes pi by 3 omega. Now put the values pi by 3 into omega. How much is the omega? This is the omega, 100 pi. So this becomes 1 by 3, 1 by or I'll say 10 by 3 milliseconds. So that is 3.33 milliseconds. Yeah, B is the correct match. Clear? Okay. Now AC voltage applied to an inductor. Now in place of resistor I am having an inductor. Now again move in the loop, write the KVL. At any instant I am saying, let us take this is plus, this is minus, the current is I like this. Now move in the loop. So I will say my E minus across the inductor in the direction of current, the drop will be there how much? Minus L di by dt. Completed the loop is equals to 0. I will say my di is equals to E by L dt. This is what? Yeah. Now put E. What is E? E is E naught sin omega t. So write it there, or sometimes we say V naught sin omega t. So don't get confused. So this is E naught sin omega t dt divided by L, and this is my di. Integrate it. Now I will be, what is this? E naught by L is constant. Integration of sin omega t is minus cos omega t by omega. So minus cos of omega t by omega. Now what else? Constant of integration. This is indefinite integration I am doing, okay? I am not putting the limits, so there will be a constant also. See, it can be 0, it cannot, it may not be 0 also. Now let us see what can we see first. Now if I say in one complete cycle, this is my alternating current, in one complete cycle its average value should be 0. If there is a constant which is non-zero, then the average value will not be 0. It means this constant must be equal to 0. Getting it? So I can say my I comes out to be just minus E naught by omega L into cos of omega t. Now this minus cos omega t I can write as, what I can write? Minus cos omega t I can write as sine of omega t minus pi by 2. Okay, so let us write it as E naught by omega L sine of omega t minus pi by 2. Sine of pi by 2 minus omega t will be cos omega t minus if you take out. Okay, therefore I can write minus of cos omega t as sine of omega t minus pi by 2. Now see this expression. What is this? This is the peak value of voltage and divided by omega L. What is this omega L? It should have some same unit as that of resistance because it is voltage divided by that. Okay, so it should have same unit of resistance only. Okay, so this omega L we define as the inductive reactance. Omega L is my inductive reactance and that we denote with XL. So I write this as E naught by XL into sine of omega t minus pi by 2. What is XL? XL is my inductive reactance. And XL is equal to omega L. Keep this in mind. So if I want to find current, what is the magnitude of the current? V naught divided by the inductive reactance. Instead of resistance, I will say inductive reactance, XL. XL is my omega into L. Now one more thing here that is important is, if you see my voltage applied was this, my current is this. There is a phase change, isn't it? My current is lagging. My current is lagging by an angle pi by 2. or in different words I can say the voltage is leading by an angle pi by 2. Okay, so when inductor is there, the voltage leads the current by pi by 2 or the current lags the voltage by pi by 2. Is this point clear? Okay, I'm writing it. For inductive circuits, purely inductive I am talking about, okay, only inductor is there. So for inductive circuits, my current lags the voltage by 90° or by 90°, or in different words if I say my voltage leads the current by 90°. This thing is very important, keep this in mind. For inductor, the current lags the voltage or the voltage leads the current. Now let us draw the phasor. Okay, so first of all, the voltage phasor will show with an arrow. This is my voltage phasor. Here this angle is omega t at a particular instant. Now the current phasor leads, current lags it by pi by 2. It means when I show the current phasor, it will be like this, lags by an angle pi by 2. This is my I node, okay, this is my V node or E node, and this angle is 90°. Keep this in mind that here my current is lagging by an angle 90°. Okay, and I naught is my V naught by omega L. I naught is my V naught by XL, which is V naught by omega L. Now let us write power. Let us write power. A very important thing to know is inductor cannot dissipate the power. Common sense says inductor cannot dissipate the power, only resistance can do, isn't it? When resistance is there, it will dissipate the power. Can inductor do? No. It can store the power, it can give the power. Okay, that only it will do. Okay, it will take and it will give, like that. Same thing with capacitor. Only capacitor is there, can it dissipate the power? No. Only resistance can dissipate. So if there is only inductor or only capacitor, the power dissipated in the circuit will be 0. We'll see that. Now see this. When I say instantaneous power, what is this? Vi. What is I? I was I naught. Okay, sine of omega t minus pi by 2, and V was, here we were using E naught, so let me write E naught only, E naught and sine omega t. So this becomes my E naught into I naught, okay, and sine omega t minus pi by 2 minus cos omega t, so minus of sine omega t into cos of omega t, and this I can write as minus E naught I naught by 2 multiply and divide with 2 sine omega t cos omega t is sine 2 omega t. So this is my sine of 2 omega t. This is my instantaneous power. Now take the average. So if I say average power, this is constant, I'll take this out, E naught I naught by 2. If you take the average of sine 2 omega t, what is that? 0. Sinusoidal function average is 0. It's not a square, it's just 2 sine. So it will be positive also, it will be negative also. So average of that will be 0. Inductor cannot dissipate power. Capacitor cannot dissipate power. Only resistance can dissipate the power. If resistance in the circuit is 0, the power dissipated in the circuit will be 0. Now, if you see instantaneous power, it's not 0. This instantaneous power is not 0. Sometime it will be positive, sometime it will be negative. Sometime the inductor will be taking energy from the source, sometime the inductor will be giving energy to the source. But overall, if you talk about how much is the net exchange, 0. Okay. Let us do some questions on this. As shown in the figure, an inductor of inductance 200 millihenry is connected to an AC source of EMF 220 volt. So this is AC source. Here he is saying 220 volt. Now the question is, he is not saying 220 sin omega t like that. Now this 220 he is saying only. So what it is? Peak value or RMS value? What it should be? RMS value. Yes, this is RMS value. This is my VRMS. By default, I should understand that this is my VRMS. Okay. And frequency 50 Hertz, the instantaneous voltage of the source is 0 volt when peak value of current is this. Okay. Only inductor is there. What will be the phase difference between inductor and current? Voltage and my current? Pi by 2. When one thing will be maximum, another thing will be 0. When current will be maximum, voltage will be 0. When voltage will be maximum, current will be 0. He is saying the same thing. Voltage is 0 and the maximum value of the current is this. What I need to find? I need to find the maximum value of the current. I need to find the maximum value of the current. What is that? I naught. So what is I naught? I naught is V naught by XL. I naught is V naught by XL. Okay. Now here we are not given V naught, we are given VRMS. How to write V naught in terms of VRMS? Root 2 times of VRMS. Root 2 times of VRMS. Okay. Now put the values. So my I naught is equal to root 2 divided by XL. XL is omega L. What is omega? 2 pi F. So 2 pi into F is 50. 2 pi F, this becomes my XL into VRMS. VRMS is 220, root 2 VRMS. Root 2 I already mentioned, so 220. Okay. Now, yeah, we can cancel what? This 0 and 2 into 11 here. Okay, 5 is also there. Can we simply, we missed something? No. Root 2 into VRMS is 220 divided by omega into L. L we missed, yeah. L we missed. This was 2 pi F, this was my omega into L. What is L? L is 220 millihenry. 220 milli means 10 to the power minus 3. So I'll take 10 to the power 3 in the numerator. Now it is fine, yeah. So this 220 is getting cancelled. 50 into 200. So 110 will remain there. Everything is fine, yeah. So this becomes root of 2 into 10 divided by pi. Okay, so what is that? This is root 200 by pi. So A comes out to be 200. Okay. No, I did mistake. This was 200 millihenry. Yeah, this was 200 millihenry. Again, I did mistake. This was 200. L was 200 millihenry. I put L as 220. No, let us put the values again from here. Clearly, let us make the things more clear. So this is root 2 VRMS divided by omega L. Okay, so what is this? Root 2 into what is VRMS? VRMS is 220 So 220 divided by omega is 2 pi into f is 50 into L was 200, not 220. This was 200. For milli, it will become 10 to the power 3 in the numerator. Now it is fine. Yeah. So what can be cancelled here? 1, 2, 3. 3 zeros. 5 into 2, 10. So this will be cancelled. And 2 into 11. Yeah. So this becomes 11 root 2 divided by pi. We'll take 11 inside the root. So this will become 11 square into 2. 11 square is 121. Yeah. Okay. So 121 into 2. 242 divided by pi. Yeah. 242. Previously I did mistake in the calculations putting the values of L. Now this is fine. I hope there is no mistake. If there is, you can tell in the comments. Now let us move ahead. AC voltage across a capacitor. Now we are taking AC source and we have connected a capacitor. Let's see. Initially, let us take at a particular instant. This is plus, this is minus. Some current I is going like this, and this capacitor is having charge plus Q and minus Q on the plates like that. Now move in the loop, write the KVL. So we'll say E, okay, plus E. Then I'm going from positive plate to negative plate. There is a drop, yeah. So minus of Q by C. This is the drop because V is equals to Q is equals to CV. V is equals to Q by C. So the drop will be minus Q by C is equals to 0 now. Here I can say E comes out to be Q by C. So my Q comes out to be E into C. Okay. So my I comes out to be integration of, no, differentiation. Yeah. So I am saying my I current. Okay. So what is Q and I, how I can relate? I is equals to dq by dt simply. I is equals to my dq by dt. So differentiate it. So I will become, C is a constant that will come out, d E by dt. What is E? E is my E naught sin omega t. Okay, so this is C E naught. Differentiation of sin omega t is omega cos omega t. Omega cos of omega t. Okay, so this comes out to be E naught. I can write omega c as 1 divided by 1 by omega c like this. Cos omega t I can write as sin omega t plus pi by 2. Why I am writing it like this, you will understand. Now this 1 by omega c, I will take this as somewhat related to resistance only. You see here I is V by, here R is there. Okay, so in place of resistance we are having 1 by omega c. Okay, so 1 by omega c whole, we take this as my another constant that we say as my XC or my capacitive reactance. Okay, there we were having inductive reactance, here we are having capacitive reactance. So this becomes my I. Okay, and this we can write as E naught by XC sine of omega t plus pi by 2, and this XC is my capacitive reactance. And what is XC? XC is 1 by omega c. So if a capacitor is there and we have to find current, we'll write V by XC, the magnitude. Okay, so whatever is the magnitude here, E naught, so E naught by XC. When inductor was there, we need to write XL. Okay, there XL was omega L, here XC. XC is 1 by omega c. One important thing to note from here is If you see, this is my voltage and this is my current. My current is leading the voltage by pi by 2. This is plus pi by 2. Okay. So, my current is leading the voltage by pi by 2. So, in I'll say in capacitive circuits, okay, in capacitive circuits, the current leads the voltage by pi by 2. Current leads voltage by pi by 2 or 90 degree. In different words, if I say the same thing, I can say my voltage lags current by pi by 2. Either my current leads voltage or my voltage lags current. This is very important to keep this thing in mind, because many times this will be used. So make sure you understand this thing. Remember this thing. Capacitor, current leaks. Inductor, current lags. You can remember it like this. Okay. Now, let us talk about the phasors and then we'll talk about the power dissipated. Okay, let us talk about the phasor. Let me take a different color. Phasor diagram. Now, important thing to see from here is that there is phase difference of pi by 2 is there. Okay, so if voltage is maximum, the current will be minimum. Okay, like when voltage is V naught, the current will be 0. When current will be I naught, voltage will be 0. Phase difference of pi by 2 is there. Okay, now drawing it, the phasor diagram. Okay, let us show the voltage. This is my voltage phasor having magnitude V naught or E naught. At a particular instant, this angle is omega t. Now, the current leads. So, when I draw the current phasor, how will I show the current phasor? Leading by an angle of pi by 2. Leading by an angle of pi by 2. So, this is 90 degree and this is my I naught. And what is I naught? I naught is my V naught divided by XC. What is XC? XC is 1 by omega C. Concepts are very small, but you need to have that clarity in your mind for the concepts. If you have that clarity in your mind, very easy to understand everything. Okay, so therefore although the small things are there, I am repeating them so that you understand nicely. So my current is leading the voltage by an angle 90 degree in this phasor diagram. Okay, now let us talk about the power. Let us write the power, and I can directly also say, because this is only a capacitive circuit, the dissipated power will be 0, because the capacitor cannot dissipate the power. Simple thing. Power. So if I write the instantaneous power, I'll say instantaneous power is equals to V instantaneous into I instantaneous. What is V instantaneous? E naught sin omega t. What is I instantaneous? That is my I naught sin of omega t plus pi by 2. Sin omega t plus pi by 2 I can write as cos omega t. So this will become E naught I naught sin omega t into cos omega t. Multiply with 2 and divide with 2. 2 sin omega t cos omega t will become sin 2 omega t. So this is E naught I naught by 2 sin of 2 omega t, and now take the average. So this is my instantaneous power. If you take the average, so average of this E naught I naught is constant, 2 is constant, take that out, take the average of sin 2 omega t over complete cycle, and that will come out to be 0. Sin 2 omega t, whatever will be the positive portion, same negative portion, average will be 0. So average power dissipated in case of pure inductive circuit or in case of pure resistive, pure capacitive circuit is 0. That point is very clear to us. Only resistance can dissipate the power. If resistance is there, the power will be dissipated, otherwise power will not be dissipated. Coming to some questions on this. The RMS value of a conduction current in a parallel plate capacitor is 6.9 microampere. The capacity of this capacitor, if it is connected to 230 volt AC supply. Now what is this 230 volt value? What is this, RMS or peak value? RMS. This is RMS. And here for current he specifically mentioned this is RMS value of the conduction current. Even if he would not have mentioned this value as RMS value, I'll be by default taking this as RMS value. Okay. Now I say that my I naught is my V naught divided by XC. So I can say IRMS also is equals to VRMS. IRMS I can denote with capital I, VRMS with capital V. Now what is IRMS? IRMS is 6.9. Anyway, first let us put XC as 1 by omega C. So if I put XC as 1 by omega C, so this will become V divided by 1 by omega C, which will become V into omega C. And from here I need to find my C, so I can say my C comes out to be I divided by V omega divided by V into omega. What is I? I is 6.9 microampere. So 6.9 into 10 to the power minus 6 divided by, what is V? V is 230. So 230. What is omega? Frequency is, okay, here they are saying radian per second. Unit is radian per second. So this is omega only. Don't say 2 pi f. Okay. So 600. And now you can put the values and solve this and put your answer in the comments. I have seen many of the students, they solve parallelly but they don't put their answer in the comments. So take a minute, put your answer in comments so that I can know who is solving the questions, who is not solving the questions. So you are spending so much energy in watching it, so make sure you mention your name also. Okay, now let us have another question further. In a circuit consisting of a capacitor and a generator with alternating EMF, this is my generator, its EMF is given to us. Okay, this is okay, so E G naught sin omega t. Yeah, VC and IC are the voltage and the current. Correct phasor diagram for such circuit is, you see, in July 2021, this is 2021 paper, and they are directly asking the phasor diagram. So we already understood what is, how to draw the phasor diagram. So we know that current will be leading the voltage. Current is in phase, current is leading the voltage by pi by 2. Current is out of phase, current is lagging the voltage. Okay, so current is leading the voltage by an angle pi by 2. Now let us talk about LCR series circuit. Now here comes my resistor also, inductor also and capacitor also, all three are connected in series, and this is one of the most important topic of this chapter. One of the most important. If you understand this thing, it means you understood almost the whole chapter. So understanding this is very important. Okay, so pay your attention, don't skip any part further. So RLC, these three are connected in series. Now, if something is connected in series, whatever current will pass through resistance, same current will pass through capacitor, same current will pass through the inductor. You You understand that? Yes. So if I say current is I here, this I will pass through resistor also, capacitor also, inductor also. How to solve this? Let us take this is my E, which is V as a function of time, and I am taking this V as V naught sine of omega t. Now there are two ways to solve this circuit. One is mathematically we can solve. Mathematically how? I'll move, write the KVL, and then mathematically analyze the equations further, solve, relate and solve. But that is a way longer method. The shortest method is the phasor diagram. Now phasor diagram is, you may say, a bit tricky to understand, but it is very simple and very straightforward. Once you understand phasor diagram, solving any question is very easy. Now see, I am doing it from phasor diagram. See what I am doing. Oh, this is dotted. This is very important to understand, so pay your attention. Pay your attention. First of all, we can draw the current phasor. Let us draw the current phasor. Why I am drawing? I know same current is passing through the 3. So let us draw the current phasor first. So current phasor, I am taking, this is my current. I don't know how much will be the phase of this, certainly not omega t, because there will, omega t is the phase of voltage, so its phase will be something different, because resistance is there, conductor capacitance is there, inductor is there, so some phase difference might be there. So let us take, this is my current phasor, and the peak value of the current as I naught, so this is my I naught. Let me write the I naughts here, I naught. Okay. Now if I ask you the drop across, okay, let me draw it a bit small because there will be too many things here, and if I draw it small it will be better. It will be better if I draw it a bit small. Let me draw it a bit small like this. Okay, so this is my I naught. Now we know that the voltage across resistance will be in phase with the current. Yes, I am saying here my drop across this is VR, across resistance, across capacitance is VC, across inductor is VL. So my voltage drop across resistance will be in phase with the current. So when I show the VR phasor, my VR phasor will be along the current only. This is my VR. Let me write with the same color. So this is my VR. Next is voltage across capacitor. Current in capacitor leads the voltage by 90 degree. So the voltage across the capacitor will lag the current by 90 degree. So VC will be lagging the current through this by an angle 90 degree. So when I will show VC, I will show it different color. Different color I can take, which one? Let us take this. So VC, when I will show, my VC will be like this. Lagging the current by 90 degree, lagging the current by 90 degree through the capacitor. So this is my VC. Now VL, current in inductor leads or lags? Current in inductor lags the voltage by 90 degree. So the voltage in inductor will lead the current by 90 degree. So this VL will lead the current by 90 degree. VL will lead the current by 90 degree. Which color I can use? Let us use this. Okay, so VL will lead the current. Okay, here I need to select which one. Let us use this one. Okay, so VL is leading the current by 90 degree. This is my VL, and this angle is 90 degree. You see, this VC and VL are directly opposite, isn't it? VL was lagging, VL was leading. So this is 180 degree here. If you see, this total angle is 180 degree. Okay. Now, when I'm moving in this loop, if I move in this loop, I'll say that my applied voltage, what is that? V, okay, whatever is my applied voltage V is equal to this my VR plus VC plus VL. Is it right? Saying like this? Yes, that is right, but not the magnitudes according to the phasors. Okay, so we have to take the angles also. We have to take the angles also. Just don't say that V naught, this magnitude is equals to VR plus VC plus VL. That will be wrong. That will be wrong. When I am saying this is my VR, this is my VC and this is my VL. If I take the resultant of these three, I will get my value of V naught. Resultant of these three in phasors with angles, okay, not just sum of the magnitudes. No, that will be wrong. So take the resultant. Now this is VL, this is VC. If you subtract that in one direction, it will come resultant. Let us take the capacity. VC is more, so it will come in this direction. That will be VC minus VL. So VC minus VL and VR resultant. That will be my V naught. Okay, let us show it again with which color? Let us take this red. So this is my difference. This is my difference. What it is? This is VC minus VL. VC minus VL. Is this visible? Yeah, VC minus VL. Okay. So this is my VC minus VL, VC minus VL and VR resultant. Taking a dotted line. VC minus VL and VR resultant. Yeah, that will be my, okay, not dotted. Again, I need to take solid line. Yeah, that will be my V naught. This is my V naught. This is VC minus VL. This length. And let us take this angle. What is this angle? Angle between my current and my applied voltage is phi. I am taking that angle as my phi. So first of all, the resultant of VR and VC minus VL is my V naught. Let us write that. So this square plus this square is equals to V naught square. So I will say VR square is equals to, VR square plus VR square plus, let us rub it, plus VC minus VL square. What is this? This is my V naught square. What is VR? VR is, I can relate with I, okay. So VR is my I naught into R. VR is I naught into R, peak value of that I am writing, okay, I naught into R. So square plus, what is my VC? VC is my I naught into XC. What is VL? That is I naught into XL. Clear? Now take I naught common here. I naught R square plus XC minus XL whole square is equals to V naught square. Now I got my I naught square as V naught square divided by R square plus XC minus XL whole square. From there I got my I naught as V naught divided by root of r square plus xc minus xl whole square. This is somewhat like I is equals to V by something in DC circuit like resistance. Okay, so this whole we call as the impedance of the circuit. Impedance of the circuit, and this impedance we denote with Z. Okay, Z. So I can say directly that my I is equals to just V naught by Z. I is equals to my V naught divided by Z. I naught is equals to V naught by Z, and here my Z is the impedance, which is root of R square plus XC minus XL whole square. This is very, very important. I related the peak values like this. If you want to relate the RMS values, RMS I denote with capital letter here. So I can say this is my V by Z. Okay. Z is the impedance of the circuit, and that become root of R square plus XC minus XL whole square. Now, you see one thing here. You observe this right angle triangle here. Okay, this right angle triangle. Now, in this right angle triangle, this is my VR, this is my VC minus VL, and this is my V naught. Okay, let us flip this and make a redraw it. Okay, let us flip this and redraw it. What was that? A right angle like this. I am drawing again. Okay, I'm in the next page. I am writing it. Okay, I am drawing it like this. One was, what was this? Hypotenuse. Hypotenuse was the resultant. This was my V naught. Okay, and this was my 90 degree. Okay, and this was my VC minus VL, and what was this? This was my VR. VC minus VL is I naught into XC minus XL. VR is I naught into R. V naught is I naught into Z. I naught is multiplying with the three sides. So what I can say, I can just take the proportionality out of I naught, and I can say in this right angle triangle, let us take this as my XC minus XL, this is my R, and this is my Z, and this is my angle phi. And this triangle we call as the impedance triangle. The impedance triangle. Okay, so in this impedance triangle, this is a right angle triangle. Okay, the hypotenuse square is equals to the vertical square by the base square. Yes, we can understand that. And phi also we can find. What was that phi, by the way? Phi was the phase difference between the voltage and the current. Yes, and I can say my 10 phi is basically equals to XC minus XL divided by R. What is phi? Phi is phase difference between voltage and current. If XC is more, current will be leading. Okay, if XC is less than XL, current will be lagging. So here phi I am taking positive for the current to be leading. Okay, is that clear? Now if I write, okay, impedance triangle I got. If I write my resultant, my initially I took my voltage to be what? V as my V naught sin omega t. This is what I took my voltage. So if I write my I will be I naught sin of omega t plus phi, where my I naught is equals to V naught by Z, where my phi is equals to tan inverse of Xc minus XL divided by R. Okay, so this is what we need to discuss that was needed for series RLC circuit. All things we discussed. Few of the points we can recap again. The voltage across the resistor is in phase with the current. The voltage across capacitor is lagging the current by 90 degree. Voltage across inductor is leading the current by 90 degree. We took the phasor of the current. Okay, this becomes my VR, this becomes my VL, this becomes my VC. The resultant of the vector resultant of these three vectors will be my V naught. I took the resultant of V naught from there. I wrote it like this and defined something that is impedance, that is my Z, and that becomes equal to root of R square plus XC minus XL square. And from there we discuss the impedance triangle also, and this is what we got. If my V is equals to V naught sin omega t, I becomes I naught into sin of omega t plus phi. Here my current is leading the voltage by an angle phi. How much is that phi? Tan inverse Xc minus XL by R. If Xc becomes greater than XL, current will be leading, it will be positive. If Xc becomes less than XL, the phi will be negative and the current will be lagging the voltage. Is that clear? Is this clear? Okay, great. If you understood it, great. You almost understood this whole chapter if you understand this one thing, because that is the crux of this chapter. Now let us do some questions on this. An AC source is connected in a given series LCR circuit. The RMS potential difference across the capacitor of 20 microfarad is, what it is asking, VC, and also it is asking the RMS value of that. Is that clear? Now what is VC? VC is equals to the current there, I naught into XC. So if I say VC RMS, so I'll say this is my I RMS into XC. Simple. This is what we need to find. What is I RMS? I RMS will be V RMS divided by Z. Z is the impedance of this circuit. That's what we need to do. Let us find first Z. For Z I need XL and XC. So first of all let us write XL. XL is omega into L. What is omega? 100. Okay, this is sin of omega t. This 100 becomes my omega. So 100 into 1. So this becomes 100 into 1. That becomes 100 ohm. What is XC? Unit of XL and XC is ohm only. Okay, what is XC? XC is 1 by omega C. XC is 1 by omega into C. What is omega? Omega is 100. What is C? C is 20 microfarad. So 20 micro, 10 to the power minus 6, that will go in the numerator, 10 to the power 6. So what it will become? This is 3, okay, 10 to the power 3 will get cancelled. So 1000 divided by 2, that comes out to be 500 ohm. Okay, now if I write Z, Z is root of R square plus XC minus XL whole square. Put the values. What is R? R is 300. So 300 square plus what is XC? XC is 500. So this is 500 minus what is XL? XL is 100. 100 square. What is 500 minus 100? 400. So 300 square plus 400 square, whole root will be 500 ohm. So this becomes my Z. I got my Z to be 500. Now let us put the value of Z here. What is VRMS? VRMS is 50 root 2 by root 2. 50 root 2 by root 2 divided by Z. What is Z? Z is 500 divided by 500. What it becomes? It becomes 1 by 10. IRMS comes out to be 1 by 10 ampere. Put it here. So VC RMS is equals to IRMS into XC. How much is XC? XC is 500. So 500. This comes out to be 50. 50. Yeah. Volt. 50 volt. Clear? Okay. So understanding each thing is very important. It's not that just you memorize one formula. I is equals to V naught divided by root of R square plus XC minus XL square, and remember this and just try to do the questions. No, you need to understand what is VC. VC is magnitude will be the current into the XC. Okay, and if he is asking the RMS value, so VRMS will be IRMS into XC. Okay, how to find the IRMS? IRMS will be VRMS by Z. Another question. In the given circuit, the RMS value of the current through the resistor is, okay, just RMS value through the resistor means through the circuit only, the same thing. So here this is the RMS value only they are giving. So I'll say IRMS is equals to my VRMS divided by Z. I need Z. Okay, finding Z is very easy because they have mentioned already XL and XC directly. So this is also sometimes very much advantage that is given. In the question they just directly mentioned the value of XC and XL. You need not find XL is equals to omega L or XC is equals to 1 by omega S. No, the units are ohm. So okay, so this is XL and this is XC. They are not giving L and C. So just put it in the value of Z. So Z is equals to root of R square plus XC minus XL whole square. Put the values. I'm writing this formula again and again such that you memorize it. I'm writing this thing again and again such that you memorize these terms. So what is R? R is my 100. Okay, so 100 square plus XC minus XL. XC minus XL 100 minus 200. 100 minus 200 square. Okay, so what it will become? 100 square plus 100 square, so that will become 2 into 100 square, so that will become 100 root 2. So I got this as 100 root 2. Okay, now I got my Z 100 root 2 ohms. This is my Z. Now put the value of VRMS 200 root 2 divided by 100 root 2 becomes 2 ampere. So the answer comes out to be 2. I am writing each step. I am not even skipping the step where I am putting the values so that you understand. And I am solving these questions parallelly only with you. So I am taking all the steps so that you understand each and everything very nicely, very clearly. I hope you are doing that. Another question. An LCR circuit contains a resistance of 110 ohm and a supply voltage of 220 at 300 radian per second. Again, I am repeating the same thing. What is this 220? RMS or peak value? RMS. Okay, that is RMS by default. If only capacitance is removed from circuit, current lags behind the voltage by 45 degree. If on the other hand only inductor is removed, current leads by 45 degree. The RMS current flowing in the circuit will be. The important thing to understand here is when only when only capacitance is removed, it means there is resistance and inductor. Only resistance is there and an inductor is there. So he is talking about this case. and current lags behind voltage by 45 degree. What is the angle between voltage and current? I'll say tan phi is equals to Xc minus XL by R. C is removed, Xc is not there. Put Xc is equals to 0. What is tan phi? Minus XL by R. And this is minus 45 degree, lags by 45 degree, okay? Therefore, minus 45 degree. Phi is minus 45 degree, not this. Phi is minus 45 degree. If you put tan of 45 degree minus 45, that will become minus 1. So, this is my minus 1. So, XL is equals to R. This thing I got from here. Next thing, when only capacitance is removed from, if only inductor is removed. Inductor is removed now when we are having a R and C. Now we are having R and C. Here they are saying that the current leads by 45 degree. So put this formula, put XL is equals to 0, tan phi again will become XC by R. This is 1, XC is also equals to R. XC is also equals to R, XL is also equal to R. The RMS current flowing in the circuit. Now, when I say IRMS, that will be my VRMS divided by root of Z R square plus XC minus XL whole square. I got X is equals to R and XL is equals to R. It means XL and XC both are equal. This will become 0. So, this is just VRMS by R. What is VRMS? 220. What is R? R is my 110. How much is this? 2. This becomes 2 ampere. 2 ampere, B option. Is this point clear? We'll come to my LR circuit and AC LR circuit, basically LR circuit and RC circuit and all those. We'll come to that. Now let us discuss LR circuit, AC LR circuit. DC LR circuit we already discussed. Now this is AC LR circuit. DC LR circuit means there with initially the inductor behaves like open circuit, finally the inductor behaves like a closed or the short circuit, okay, and the current reaches a steady state. That was my DC LR circuit. Here this is AC. So C is not there. C is not there. Only resistance is there and only inductor is there. So when I write the impedance here Z, which used to be under root of R square plus XC minus XL whole square, C is not there. It means put X is equals to 0. This is my 0. So my Z here becomes root of R square plus XL square. My current I naught will be V naught by Z. My tan phi will be XC minus XL by R. XC is 0, so minus XL by R. Okay. And you can draw the impedance triangle also here if you want, just showing you. Oh, not this way. Okay. So this is my XL, this is my R, and this is my Z, which is root of XL square plus R square. This is my phi. And if you want me to draw the phasor also, I can draw the phasor diagram quickly. Let us draw the voltage phasor. First the current phasor I am drawing. This is my current phasor, okay, and the voltage across the inductor will be in phase with the current. VR will be in phase with this current. Let us show that. So this becomes my VR, okay, and my second, that is VL, the which color? Let us take this. So VL will be leading the current, Okay, VL, the drop across the inductor leads the current by 90 degree. So this will be my VL. It's just a quick revision. I'm doing this same thing again. Okay, so VL, VR, and this was my, okay, I did a mistake. This was my VL, and that was my VR. And the resultant of the two, how to show that? Let us take the resultant, not an arrow, I need a straight line. So the resultant of these two, this, I missed it, yeah, so this is my V naught, this was my I naught, this here the it is leading, the voltage is leading the current phasor. So my phi, I took the phi positive on the other side, so therefore it is negative, minus XL by R. And if I want to write the equation of the current, so I'll say my current will be my voltage V naught by Z into sine of omega t minus this angle, what it is, okay, plus phi only I am writing here, but I have considered negative sign here, so that negative will be considered there. So there is no difference between this and what we discussed in series RLC circuit. Only put x is equals to 0 everywhere. Put x is equals to 0 everywhere, same thing you will get. Z also put x is equals to 0. Phi equation also 10 phi, put x is equals to 0. In phasor also put x is equals to 0, Vc becomes 0. That's all. Now coming to some questions on this. Let us read the question. A coil of negligible resistance is connected in series with a 90 ohm resistor across 120 volt 60 hertz supply. A voltmeter reads 36 volt across resistance. Inductance of this coil is. Okay. Now resistance is given. Yes, that is 90 ohm. So this is 90. And inductor is there across a supply which is 120 volt and 60 hertz. Okay, and what else? Yeah, the voltmeter reads 36 volt across resistance. So across resistance, what is this? This is 36 volt. Total is 120, across resistance is 36. How much will be across inductor? 120 minus 36. No, that is incorrect. See again. VL and VR are perpendicular to each other. So my resultant V naught is root of VL square plus VR square. Understand this. So when I say my resultant 120 is root of 36 square plus VL square. Everything is in RMS, okay? This is RMS, this is RMS, this is RMS. Getting it? So from here you will get VL. From here you will get VL. Now whatever is the current through resistance, same current is passing through the inductor. How much is the current through resistance? Voltage across the resistance divided by the resistance. So I will say VR divided by R, that is my 36 divided by 90. Same current is passing through inductor also. So when I will say my VL, whatever VL I will get, I will say my VL is equals to I into XL. Okay, VL is I into XL. So my XL will become VL divided by I. I got my VL from here, I'll put the VL here. I got my I here, I'll put I here. I'll get XL, and XL I'll put as omega L. From there, I'll solve for L. Some calculations are there. I have mentioned the steps. Now I want each one of you to solve this. First of all, the steps are, first of all, you got the I. Okay, first of all, you find VL first here, get I from there, put I here, put VL here, get XL. Once you get XL, put that equals to omega L. And what is my omega? What is omega? Frequency is 60 Hertz. So omega is equals to 2 pi f. Remember this always. 2 pi into 60. So this is 120 pi Hertz. Put that omega here. You will get what is L in Henry. Solve this. Take a pause. You can pause this video, solve it, put your answer in the comments. Then we'll move ahead. Do it quickly. Okay. Now, RC series. Let us talk about RC series. Here, my XL is 0. Only resistance is there, and only capacitance is there. Same exercise again. What I'll say? I'll say my again. Let us write Z. That is root of R square plus XC square. My 10 phi. That will be just XC by R. If you have to draw the impedance triangle, you can draw it again. This is my XC, this is R, this is Z, which is root of R square plus XC square, and this angle is 90 degree. Okay, this angle is my phi. If I want to write the current here, voltage is like V naught sine omega t. If I write the current, it will be I naught, which is V naught by Z. Okay, let us write that as V naught by Z. V naught by Z into sine of omega t plus phi. This is my Z. We can draw the phasor also. Again, the same thing. I am doing this such that you understand everything. Again and again I am doing the same thing. You see. First of all, let us draw the current. Let us take the current. This is my current I. Okay. The VR, the drop across the resistor, will be in phase with the current, and therefore I will show my VR to be like this. This is my VR. Okay. VC will be lagging the current by 90 degree. Then I will show the VC lagging the current by 90 degree. I will show it like this. This becomes my VC, resultant of these two. Now a dashed line I need. So resultant of these two vectors, VR and VC, that will be this. Okay, this will be my resultant. This is my V naught. Getting it? And what else? This is angle. This is my angle phi, angle between V naught and my I naught. This was my I naught here. Okay, everything else is the same. So just put X is equals to 0. What exercise we did for RLC circuit, in that put XC is equals to 0, you will get sorry, not XC, XL. Here we are having capacitor. Put XL equals to 0, you will get the same result. Everything else will remain the same. Getting it? Okay, now we are having a question. This question was asked in 2021. An RC circuit has, as shown in the figure, is driven by a AC source generating square wave. Now this is not a sinusoidal case, this is a square wave case. The output wave pattern monitored by CRO would look close to. Okay. So how the output wave pattern means the voltage across the capacitor will vary. Here this is a resistor, this is a capacitor, you can say. This is my closed circuit. Okay. Here I am having a resistance. The diagram is a bit like different here. Okay. So this is my capacitor here, and we are seeing the voltage across the capacitor, how it is varying. Now square wave is coming. Square wave will be like this, plus, then minus V naught, then plus V naught, then minus V naught. So when plus V naught will come, capacitor will charge. Minus V naught will come, capacitor will discharge. Isn't it? Same thing. So charge, try to, it will not be attaining a steady state, but it will try to attain a steady state, then discharge. Okay. Charge, then discharge. So, and discharging also will be sudden, or it will be like, you know, RC circuit discharging means slowly it will discharge like this. Okay. So it will not be sudden like this. Charging, discharging, then charging, then discharging. So D is the correct option. We just need to see which is nearly the possible wave. Okay. Yeah. Okay. Now LC series, we are having only L and C. Here we are not having our resistance. So put R is equals to 0. So here if you see Z, so Z will be equals to root of XC minus XL whole square. When I say current, I will be equals to I naught is equals to V naught divided by Z. Okay. And certainly here my R is 0. So when I say 10 phi XC minus XL by 0, so that is pi by 2. Okay. So the angle between my current and voltage is pi by 2. So phi is equals to a plus minus 90 degree depending upon which is greater, XL is greater or XC is greater. And if you want to draw the phasors, let us do the exercise again. So let me show a bit here. Okay. So first of all, some current will be here. Let us draw the current phasor. First of all, the current phasor we draw. Current will be same in both the cases. So this is my current. Let us write it as my I naught. The voltage across the capacitor will be lagging by the current by 90 degree. Voltage across inductor will be leading the current by 90 degree. So voltage across capacitor and inductor. There is a solid line. Yeah. Voltage across capacitor. This is my VC. Voltage across inductor. Sometimes I get confused which one to select. So yeah, this is my VL, this is my VC, this is 90 and 90, these two. Okay, so VC minus VL will be somewhat in this direction. You can take the difference of that will become my VC minus VL. So this will be my VC minus VL. Okay, and the resultant of VC minus VL, okay, wait a minute, resultant of VC minus VL will be my VT. There is no VR. So this is my VC minus VL, and this will be equal to my V naught, not VT, V naught, the peak value. Here VT is V naught sine omega t. And if I write my current, I'll say I is equals to V naught by Z sine of omega t plus phi. Phi is plus minus 90 degree. Simple. Is everything clear? Okay. Some question on this? Yeah, let us discuss. In LC circuit, the inductance L is 40 millihenry and capacitance 100 microfarad. If a voltage that is 10 sine of 314t is applied to the circuit, uh, to the current in the circuit is given by, here 2 will not be there. Okay, the current in the circuit is given by, LC circuit is there. Okay, so simply I'll say, first of all, let us write my XL and XC first. Okay, so what is XL? Omega into L. What is omega? Omega is 314. This is omega 314 into L. What is L? L is 40 millihenry. So 40 into 10 to the power minus 3. What is XC? 1 by omega C. What is omega? 314. What is C? C is 100 microfarad. So 100 micro means 10 to the power minus 6. So it will become 10 to the power plus 6 in the numerator, this much ohm. XCXL we got. Okay, and from there we can see which one is greater, which one is lesser. Okay, that point is clear to you. So I'll say my I is equals to V naught. What is that? What is V naught? V naught is 10. So 10 divided by Z. Z is root of XC minus XL whole square into sine of 314 T plus phi. What is phi? Phi is, I'll say, plus minus 90 degree. If XC is greater than XL, phi is 90 degree. If XC is less than XL, phi is minus 90 degree. Why I am saying this? Because you know 10 phi is equals to XC minus XL by R. R is my 0. It means this becomes infinity. If XA is greater than XL, it will be plus infinity. If XA is less than XL, it will be minus infinity. Plus infinity means phi is pi by 2. Minus infinity means phi is minus pi by 2. Okay, just put and then see which option is correct. I am not getting into calculations. I want all of you to pause this video here, solve this question, put your answer in the comments and then come back. I hope you are back. Okay. You will get benefit of these videos only when you are focused, only when you are solving the questions parallelly. If you see, sir, I know all these things, I am just revising it. Okay, just keep on going. I am not going to solve. So you certainly will be benefited, but not that much. If you want full benefit, means you need to solve the questions parallelly with me. I'm drawing the phasor diagram. You draw the phasor diagram yourself also. Okay, solve the series RLC circuit, drawing the phasors and finding all the things. It will become crystal clear in your head how we are showing VC, how we are showing VL, how we are showing VR, how we are showing the current phasor, how we are showing the voltage. Any question you can solve very quickly. Okay. Now, average power in series AC circuit. So when we say power, instantaneous V into I, instantaneous value V into instantaneous value of the I. This is how we write. What is V? V is V naught sine of omega t. We took, what was our I? I was I naught sine of omega t plus phi. So I say instantaneous value comes out to be V naught into I naught into sine of omega t into sine of omega t plus phi. Let us multiply and divide with 2. It's not looking proper. Okay. Now this term 2 sine omega t plus phi, what is that? 2 sine A sine B, what is that? Cos of A minus B minus cos of A plus B. Yeah, let us write it. So this is V naught I naught by 2 into cos of A minus B, so cos minus phi cos phi minus cos of A plus B omega t, 2 omega t plus phi, it will become A plus B. Everything is fine? Yeah. So this becomes my instantaneous power. I need average. Okay. In AC circuit, when we say power, by default it means average power. So take average, so I'll say P average, taking average on the right side, V naught I naught by 2 is constant, take that out, V naught I naught by 2, average of cos phi is a constant or variable, phi is constant, it will not change with time, so cos phi average is cos phi only. What was the average of cos 2 omega t plus phi? 0. Average of this term is 0. Average of this term is 0. Why so? Because whatever be the positive part, same negative part will come in the complete cycle. So average of this is 0. So this becomes V naught I naught cos phi. I got this formula for power. So I say this as VRMS into IRMS. So I can just say VI cos phi. I am denoting VRMS with capital V, IRMS with capital I. So power formula becomes VI cos phi. We will talk about this again. Power formula becomes VI cos phi. Can we simplify it further? Yes, we can simplify. What is V? V I can write as I into Z, isn't it? I can write V as I into Z, IRMS into Z. So this will become I into Z. So I square into Z cos phi. What is Z cos phi? Don't remember? Let us see. Again, going to the impedance triangle. In series RLC circuit, going to the impedance triangle. What is Z cos phi? Z cos phi is my R. Z cos phi is R. Keep this thing in mind. Now coming back. Z cos phi we got as R. So I got this as R. What is this formula? I square R. This was same for DC circuit also. The power dissipated was I square R. Same formula we are getting here, I square R, isn't it? Yes, we are getting the same formula. Keep this in mind. Power dissipated in AC circuit is I square R, just a DC circuit formula. Now we have to see the similarity between DC and AC. If you see that similarity, then solving AC circuits will be very easy for you. Okay, power dissipated in AC circuit, in DC circuit is I square R, in AC circuit also I square R, provided that I is my RMS current. Yes, that I is my RMS current. Okay, so my power dissipated becomes, I can write in different terms also, different forms also. In terms of V also I can write, I can put I as V by Z, so this will become V square by Z into cos phi also. Okay, so that way also you can modify. Like I know for DC circuits we know power is equal to VI, and V is equal to IR, we write it becomes V square R, I square R, and if I write I as V by R, it becomes V square by R, same thing. Okay, got the formula. Now power factor. So we got power as V I cos phi. This cos phi we say this is my power factor. This cos phi is our power factor. What was phi? Phi was the phase difference between current and my resistance. Sorry, what I am saying, current and my voltage. Phi is the phase difference between current and the voltage, and we wrote the formula for phi as tan phi is equals to XC minus XL by R. From there I can find phi and I can find the power factor. So in many times the question is for the following following AC circuit, find the power factor. So then what you can do is quickly find tan phi. Okay, from tan phi you can find cos phi. You are having a question on this? Okay. Now in an AC circuit, voltage and current are given by this and this. Okay, the average power dissipated in one cycle is, average power is V I cos phi. What is V? VRMS. VRMS is 100 by root 2. What is I? IRMS. IRMS will be this peak by root 2, 100 by root 2 again. Cos phi. Phi is angle between V and I. How much is the angle here? Pi by 3. So cos of pi by 3. How much it is now? This becomes 2. This is 50. Yeah. This is also 1 by 2. So this is 50. 2500. And this was in milliampere. So 10 to the power minus 3 will be there. Milliampere was there. So here 10 to the power minus 3 will be there. So this becomes 2.5 watt. 2.5 watt, which is option C. Directly it was given what is phi. Expression is given, I can just see phi from there. Okay. Now in this question, previous, if you see, if you do a mistake and you write formula power, I know the formula Vi cos phi, but you forgot that V and I are RMS value and you put the value of peak values, you'll get 5, and that option is also given 5. You'll get 5 and that option is already given because they know where the student will make the mistake. So that option will be there in the question. So make sure you are clear with the concepts. Now another question on this. A series AC circuit containing an inductor, a capacitor, a resistor is driven by an AC source of 24 volt 50 hertz. What is 24? RMS value. The energy dissipated in the circuit in 60 seconds. So how will I write this? Now power formula I know, I square R, I RMS square R. So heat dissipated will be I square R into T. Basically I need I. For I need Z because I is equals to V by Z. V is given as 24, Z we need to find. How to find Z? Inductor is given, capacitor is given, resistance is given, we can find. So first we can find XL. So let us write XL. XL will be omega L. What is omega? 50. 50 into L. L is 20 millihenry. Everything is fine? Yeah. This becomes 1. What is XC? XC is 1 by omega C. Oh, I did a mistake here. What is that mistake? This was 50 hertz. Omega is not 50. Omega is 2 pi into F. 50 into 2 pi. I did that mistake. Make sure you don't repeat. How much it is now? 2 pi. Okay, XC is 1 by omega C. So 1 by omega is 100 pi and C is 120 microfarad. So 120 micro I will take in the numerator 10 to the power 6. R is given as 60. So I will write Z as root of R square plus XC minus XL whole square. Okay, R is 60, XC and XL I got. I'll put my value of Z here. From there I'll get I. I'll put my value of I here. R is 60, time is 60 seconds. Put that, you'll get the answer. So do these calculations. Stop this video here. Do these calculations, then come back. You can resume from there. Okay, I hope you are back. Make sure you put your answer in the comments. Now how to put your answer in the comments? You can put the timeline, like I am discussing this question in these many hours, these many minutes. Put the timeline, then put your answer. That will be the best way to mention your answer in the comments. Okay. Now let us talk about the wattless current in AC circuits. So when I say power, power is basically Vi cos phi. Okay. Let us draw the current and voltage phasor. So I am taking that, let us take, okay, let us take this is my voltage. Oh, I did a mistake. Let us take this is my voltage phasor V. Okay, and my current is leading by an angle phi. Different color, yeah. Current is leading by an angle phi. This is phi. This is my I. Now this current has two components, one along the voltage, another perpendicular to the voltage, isn't it? Yeah. So this is my I cos phi, this is my I sin phi. The component of the current which is in phase with the voltage is dissipating the power, V I cos phi. Getting it? The component of the current which is in phase with the voltage is dissipating the power, V I cos phi. The component which is perpendicular to the voltage, that is not dissipating the power, that is not responsible for dissipating the power. Therefore, that component we call as the Wattless current. So here my I sin phi is my Wattless current. That is my Wattless current. Okay. And here you see that this Vi, here these are RMS values. Okay, when I am saying power, this V is RMS, I is IRMS. So these are RMS values. Okay, so these are RMS only. So this is my RMS. So I sin phi is my Wattless current. I cos phi is not Wattless, that is dissipating the power. Okay, let us read this question. A Wattless current flows in AC circuit, then the circuit is. Now when the Wattless current will be there? If there is no resistance in the circuit, isn't it? Then only Wattless current will be there, perpendicular to the voltage always. Okay. So when there is no resistance, purely resistive circuit, no, it is having resistance. Purely inductive circuit, yes, it is not having resistance. Purely LCR circuit is having resistance, and RC circuit is having resistance. So B, purely inductive circuit. Now let us talk about parallel AC circuits. There are not many questions from parallel AC circuits in mains, and this is not specifically, you may say, that much required to understand, but a brief understanding of parallel concept is much required, because few of the times some circuits are given in the exam which are having a few, let us take some inductor, some resistor in parallel with some capacitor resistor like that, or some of the two are in parallel. So sometimes they are given like that. So I am saying that we will not go into much detail of this, but we will understand the crux of this, that is required for us. I am not going to get into too much detail of this particular topic. So a parallel RLC circuit, here if you see, if this current is I, so this current IR, this current is my IL, and this current is my IC. This current I will be vector resultant of these three phasors, not just the resultant. Don't say that my I is equals to IR plus IL plus IC and I am using junction rule. Okay. No, here when you are using junction rule here, just don't add the magnitudes. They are at different angles. You need to consider that angle also. Understanding that? Yes. So you have to take the phasor resultant of IR, IL and IC to get the resultant current I here. If I say IR, what will be IR? I am saying Vt as my V0 sin omega t. So let us, I am writing the peak values. Okay, let us write the peak values or general expression. Let us write the general expression. What is VR? Battery I know, across it the resistance I know. I can write the current as V0 by R sin omega t. Okay. Then next, if I write IL, current through inductor will lead or lag? Current through inductor will lag by pi by 2. So V naught by XL into sine of omega t minus pi by 2. Current through capacitor will lead by an angle pi by 2, therefore like this. Now take the resultant of all these and that will be my I. So here my I is equals to IR plus IL plus IC, and you write it, it will automatically become that. You can do by phasors also. Now let me show you by phasors here. Let us draw that. Here my reference will be my voltage phasor because voltage is same across the three. So let us draw the first voltage phasor. First let us draw the voltage phasor. I will take yellow color. Let us take, this is my V naught. This is my V naught. So now I am drawing the currents. So what will be IR? So IR will be in phase with this VR. So that is V naught by R sin omega t only. Okay, in phase with this VR. How will we show? Let us take this color and should I make it a bit bigger? Okay, anyways, this is my IR. Peak values, okay, peak values it means there. I can show with capital. IR. Okay, now what is IL? That current will be lagging, isn't it? Yeah, current lags. Yeah, so that will be lagging by an angle pi by 2. Which color I can use? Let us use this. IL. Capital I, this peak. And my IC will be leading the voltage. Now which color? Let us take this. IC will be leading by pi by 2. This is my IC. The resultant of these three. Okay, so subtract them. So this will become somewhat like IC minus IL. Now the resultant of IC minus IL and IR. Let us take a dotted line. Resultant of IC minus IL and IR. Which color? Let us use yellow itself. So not a dotted one, solid. So this becomes my I, total current. So if I write the peak of total current I naught, that will be my root of IC minus IL whole square plus IR whole square. And you can write this in terms of V naught. V naught into 1 by XC minus 1 by XL square into 1. V naught I can take out anyways. Okay, so this is plus 1 by R square and this is into V naught. Okay, V naught is out here, so this becomes my I naught. So we know that I naught is equals to V naught by Z. So 1 by Z is basically this. So I got my 1 by Z is equals to 1 by XC minus 1 by XL whole square plus 1 by R square. You may say, sir, I am not getting phasors and all. Don't understand the Phasor if that is not required. Just try to understand this thing, that this current will be sum of these three currents. Okay, the resultant of these three currents considering the phase also. And you see it's something like, root, I forgot. You see this formula, parallel resistance combination is there, then when we used to say that 1 by R parallel is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Something similar, isn't it? Yeah. Okay. Let us do some question. In the given circuit, the AC source has omega is equals to 100 radian per second. Considering the inductor and capacitor to be ideal, what will be the current I flowing through the circuit? Okay, how much current is flowing? So I know that the current that will flow will be the resultant of this current plus this current. So individually you can solve. Just forget this first. Okay, this is 200 volt source. Find what is the current. Then forget these two. This 200 volt source, find this current, take the resultant of these two, isn't it? Yeah. So first of all, for this above I am saying, let us find XC. How much is XC? That is 1 by omega C. So 1 by omega is 100 into C is 100 micro. So 10 to the power 6 will go in the numerator. This comes out to be 100 ohm. XC is 100, R is 100. How much will be the current? For this I am saying my Z is equals to 100 root 2, root of 100 square plus 100 square, Z1, okay. So this is 100 root 2, 100 root 2, and my phi, 10 phi is equals to XC minus XL by R. XC is 100 by XL is 0, okay. XC minus 0 divided by R is 100, so this is 1. So this means phi is 45 degree. So it is leading the voltage by 45 degree, okay, and how much is the value? That is V naught by Z, that is V naught by Z. So 200 divided by 100 root 2 and at an angle of plus 45 degree from the voltage. I am taking voltage as reference, so I can show it like this. So how much it is? To root 2 and at an angle of 45 degree. Okay, now second one. How much is XL for this? XL is omega L. XL is omega L. How much is omega? Omega is 100. So 100 into 0.5, that comes out to be 50. So Z comes out to be 50, 50, root of 50 square plus 50 square, 50 root 2. My 10 phi, if I say, is equals to XC minus XL by R. XC is 0 minus XL. XL is 50 divided by R is 50. So this is minus 1. So here my phi is minus 45 degree. So current will become V by Z, 200 by 50 root 2. 200 by 50 root 2 at an angle of minus 45 degree. 200 by 50 root 2 is 2 root 2. So this becomes 2 root 2 at an angle minus 45 degree. This is root 2 at an angle 45 degree. This is 2 root 2 at an angle minus 45 degree. They are perpendicular to each other. Yes, they are perpendicular to each other. Plus 45 minus 45. If you want to find the resultant, under root of 1 square plus 2 square. Isn't it? Like two vectors are perpendicular. If you want to find the resultant, root of a square plus b square. Yes. So take the resultant of these two. So this will become root of root 2 square is 2 plus 2 root 2 square is 8. So this becomes root of 10, and that 10 is nearly 3.1. Yeah, 3.16. B is correct. See the solution again. How I took the resultant. These two currents I got, they are at 90 degree from each other. From there I took the resultant. Need not draw the phasors. Generally when we solve the questions, we don't draw the phasors. Phasors gives you understanding of the circuit. For derivation we use. Generally, unless until the question is, let us take of advanced level, some difficult question is there, okay, some multiple things are there, then you may need to analyze the things properly, then you may need to draw the phasors. Otherwise, while solving the questions, I can just see it is plus 45 minus 45, take the resultant. Okay. Now resonance in LCR series AC circuit. If I ask you, this is my LCR series circuit, what is the value of current? You'll say the current is equals to, this I am saying as V naught sin omega t. So you'll say current is equals to V naught by Z. Z is R square plus XC minus XL whole square into sin omega t plus phi. This will say. What is the peak value of this? If I ask you the peak value, you will say I naught is equals to V naught by Z. This is the peak value. When this peak value will be maximum? How to maximize this? Can you maximize the numerator? No, V naught, that is constant. That cannot be maximized. Can you minimize the numerator, denominator? Yes, we can minimize. How? R is, that cannot change, that is constant. XC and XL, they can change with omega. Yes, they can change with omega. So I can set my omega such that XC becomes equal to XL in a circuit. Now this is the given circuit. I can change my omega so that XC becomes equal to XL. If XC becomes equals to XL, then I naught will be maximum. Okay, so I naught will be maximum, or I'll say, let me write, I naught will be maximum when my XC becomes equal to XL. When XC becomes equal to XL, this condition we say the resonance condition in the circuit. XC becomes equal to XL, and here my I naught maximum becomes equals to V naught by R. It just behaves like a resistive circuit, and phi will become 0. Phi will become 0, isn't it? Because phi, tan phi is XC minus XL by R. Tan phi is XC minus XL by R. XC is equals to XL. Phi becomes 0. The current is in phase with the voltage. So it just behaves like only resistance is there in the circuit. Okay, so that particular condition we say the condition of resonance. So this becomes my resonance condition. When XC will become equals to XL, XC is 1 by omega C, XL is equals to omega L. Let us take omega is my omega naught. So omega naught comes out to be 1 by root of LC. 1 by root of LC. So this becomes my resonance frequency, angular frequency certainly. Okay, if frequency is saying omega is equals to 2 pi f, so it will become 1 by 2 pi into root of LC. Okay, so this is my resonance angular frequency. And if you write the resonance frequency f naught, that is omega naught by 2 pi, so that will be 1 by 2 pi root LC. So this is my resonance frequency. Current becomes maximum there at resonance. XC becomes equal to XL. For that we got my omega to be 1 by root LC. So if I have, let us take an option to change omega, I can change omega and I can adjust it such that the current becomes the maximum. So that condition will become my resonance condition when XC is getting equal to XL. Okay, now let us discuss some questions on this. In series LCR circuit, the capacitance is changed from C to 4C. To keep the resonance frequency unchanged, the new inductance should be. Now, omega is 1 by root LC. Product of LC should be same. If C becomes 4C, L should become L by 4. Then only the product of LC will become same. So, L should become my L by 4. So, the new inductance should be reduced to 1 L by 4 or reduced by 3L by 4. Yeah. Yeah, there is a typing mistake. This should be 3 by 4. Either it is, when I mention the statement, therefore I am saying, so sometimes there is some confusion of the words. You see, either it is reduced 2L by 4 or reduced by 3L by 4. Reduced by means how much is the difference? 3L by 4. Reduced to means how much is the final value. So reduced to L by 4 or reduced by 3L by 4. C is the option. Okay. Now some statement question. Maximum power is dissipated in a circuit containing an inductor, a capacitor and a resistor. Now what is the power dissipated? I square R. You know the formula. When I will be maximum? At resonance. Okay. Now a capacitor resistor connected in series with AC source when resonance occurs. Yes. I will be maximum at resonance means the power dissipated will be maximum when resonance occurs. Yes. Second statement, maximum power is dissipated in the circuit containing a pure resistor due to zero phase difference between current and voltage. Vi cos phi. Phi is 0, cos phi is 1. Power dissipated will be maximum. So I will say both the statements are true. Both statement 1 and 2 are true. C option. Clear? Another question. A 110 volt 50 hertz AC source is connected in the circuit shown. The current through the resistance 55 ohm at resonance in the circuit will be. Now when resonance will happen in this circuit, my XC will become equal to XL, isn't it? So XC will become equals to XL. What is the impedance of this part? This part only. These two are in parallel. You know, the for parallel circuit 1 by Z square was equals 1 by R square plus 1 by XC minus XL, that square. You remember that? Let me show you again. What was that? Yeah, this expression, finding the parallel impedance. Okay, now coming back there. So when I say only Z of this, so 1 by Z is equals to 1 by XC minus 1 by XL whole square root. When I will say like this, X is equals to XL means this is 0. So 1 by Z comes out to be 0 when X is equals to XL. 1 by Z comes out to be 0. It means my Z tends to infinity. If Z tends to infinity, this resistance is infinity, how much will be the current in the circuit? 0. Therefore, my I will tends to 0. So the current in the circuit will be 0 ampere at resonance condition. Now the next topic, that is sharpness of resonance and quality factor. So sharpness of resonance. Now this is my peak value of the current I naught versus omega. So I naught is changing as omega is changing because XL and XC will change. I is equals to my I naught is equals to my V naught divided by Z, which is root of R square plus XC minus XL whole square. So when omega will change, XC and XL will change, my I naught will change at a particular value. When omega naught is equals to 1 by root LC, resonance will happen, and that particular value, the current will be maximum, and that will be equals to my V naught by R. That is clear to us. Now sharpness means how much this curve is having sharp. How much sharp is this curve? Means what? Like with what greater you can say what greater slope. Yeah, what greater slope it will decrease here. Means as I'm increasing my omega or decreasing my omega, okay, greater it falls, it means greater it will be sharp. It will be like a edge. Okay, it will be like an edge, isn't it? Like if you change omega slightly from here and it falls rapidly, then you will say this curve is a sharp. This curve is a sharp, isn't it? Yeah. So that factor we say the sharpness of the resonance curve, or we say sharpness of the resonance, and then we'll talk about quality factor also. Okay. So quality factor means greater the sharpness means greater the quality factor. How the magnitude of this quality factor is defined, we will talk about. So quality factor, we say this Q, this is voltage across the inductor or capacitor at resonance divided by the my applied voltage. Okay. So voltage across my inductor or capacitor, because they are the same, divided by applied voltage. This is how this quality factor is defined, and you can say this is equals to my I into XL, and this is V is equals to IR at resonance. I is getting cancelled, so this is XL by R. This becomes my quality factor Q. Okay. We can find this quality factor other way also from curve, from this graph. So what I am saying is, let me see when this I becomes 1 by root 2 times of its peak value. 1 by root 2 times means V naught by root 2 R. Root 2 R is outside. R is outside. Okay, V naught by root 2 R. When it becomes here. Okay, let us take this change is delta omega, this change is delta omega. So I define my quality factor Q to be omega naught divided by 2 delta omega. Omega naught divided by my 2 delta omega. This is how it is defined, and if you try to find numerically and solve it, it will come out to be the same, XL by R, where XL is the my omega naught L. Okay, here my XL is omega naught L. Okay, this is XL at resonance. You may write this as omega naught L only, so you may get confused. Okay, getting it? So omega naught is my resonance angular frequency. The angular frequency where the resonance happens. Let me write it in a better way. Resonance angular frequency. Now you need not go into much detail of this sharpness or quality factor. When you will do engineering, you will understand these concepts in way more detail. You just try to remember this one formula. Q is equals to omega naught L by R. I can write this formula in terms of C also. I can write omega naught as 1 by root LC, and that will give us root of L by C into R. Omega naught, if I put as 1 by root LC, yeah, it will become like this. So I can write Q like this also in terms of LC and R. Okay. So just memorize this formula. That's all. Quality factor means omega naught L by R. That's all. So write it, this formula in your notebook. Make sure you remember it, because what happens is, it's not very frequently asked, but if let us take it is asked, so there is no variety in this. It will be just a formula based question. Now a resonance circuit having inductance and resistance of this, okay, respectively oscillates at 10 megahertz frequency. The value of quality factor of this resonator is, resistance is given to us and inductance is given to us, and the omega naught is given to us. So just write quality factor as omega naught into L by R. What is omega naught? 2 pi into F. 2 pi into F. What is F? 10 megahertz. Mega means 10 to the power 6, so 10 to the power 7. 10 megahertz, yeah, 10 to the power 7 into L. What is L? L is 2 into 10 to the power minus 4, yeah, divided by R. What is R? 6.28. So 2 pi is 6.28. This becomes 2 into 10 to the power 3, that is 2000. So my quality factor is 2000. Therefore, I am saying that if the question comes, there cannot be any variety. The questions are very less asked, but if it comes, there is no variety. Just remember this formula, Q is equals to omega L by R, omega naught L by R. Now the next portion, next topic of this chapter, that is transformer. My LC oscillations I have covered in electromagnetic induction. Okay, if you are you may say, sir, where is LC oscillation? I have covered that previously, so therefore I am not covering that again. LC oscillations I have covered in detail in electromagnetic induction video, so you can watch that. So a transformer is, what is basically the purpose of transformer? Now transformer purpose is to increase or decrease the potential level, okay, of AC source. Like if let us take some AC voltage is there, okay, and that is of 220 volt. Now you want higher one, you want let us take 11,000. So what you need to do? You need to use a step up transformer which will convert your 220 to higher value of the voltage. And let us take, if you want to decrease that, then you need a step down transformer. Why this transformer is used? Now the point is, when we transmit electricity from one place to another place, let us take, electricity is generated somewhat 1000 kilometer away or 100 kilometer away, and it is consumed here. Now when the electricity will come from there, there will be losses. Yes, there will be losses. Resistive losses will be there. Okay, resistance is there, so resistive losses will be there. So now what we want is, we want to reduce those losses. To reduce those losses, we need higher value of voltage. So we are doing transmission at very high voltages. If you have seen those big towers, okay, which are having very thick wires and very like thick and long wires kind of. So but the voltage level there is very high. The voltage level is very high there, therefore the height is also way greater, because there will be magnetic field and all those things. So to reduce that, the height is kept way higher, the ground clearance is maintained there because the voltage is high. Now when that very high voltage transmission lines are coming, can we consume that at our homes? No, that is not possible for us, because our devices are at 220 volt like that, isn't it? So what we need? We need a step down transformer. So where we are generating, we will use step up transformer. Where we are consuming, we will use step down transformer. So step up, transmit at higher voltage, then step down, then consume. So this is what is done. Need not go into much detail, and this was just an idea so that you understand the purpose of transformer. So let us take, this is a transformer. Here this is our primary side, this is our secondary side. On primary side we are having some source. On secondary side we are putting our load. Now let us take flux phi is passing here. So whatever flux is passing through the primary windings, the same flux will pass through the secondary winding. Now here I am saying that the number of turns to be N primary, here the number of turns to be N secondary. What is this EMF across the primary side? So you will say it will be minus N primary into d phi by dt. So E primary is my minus N primary into d phi by dt. What is this EMF on the secondary side? E secondary. So E secondary or V secondary, sometimes we may use V also, so don't get confused. So V secondary is minus N secondary into d phi by dt. Phi is the same. Divide these two. So the ratio of these two voltages, primary by secondary, that becomes equal to the turns ratios. Should I use V secondary, V primary? Okay, anyways, you may use that also. Okay, thus I can say my V primary by V secondary. Okay, this primary and the secondary side. Here now There will be some you can say resistance of primary winding also. There will be some you can say here also some losses. There may not be 100% coupling. Okay, some resistance of winding also. Okay, that the flux is passing through this, and on the secondary side also some resistance and all those losses will be there due to that. But we are not going into much detail, because transformer in much detail is covered in electrical engineering. So I did electrical engineering from IT Roorkee. So there we studied transformer in great detail. Okay, in great detail. So all the losses, what are the winding losses, okay, what are the core losses, and then drawing the equivalent circuit of the transformer, then finding the efficiency of the transformer. There used to be bulky questions. Okay, so but that is not required at our level. So this ratio of primary voltage by secondary voltage is equal to primary turns by secondary turns. This is clear to us. Now if I say the efficiency of this transformer is 100%, which is ideally we consider, it is not always, it is not like 100% is not possible, but if we consider, okay, so if efficiency is 100% means no loss, then power input will be power output. Let us take this current is I primary, this current is my I secondary. So I'll say V primary, I primary is equals to V secondary into I secondary. So my I primary by I secondary comes out to be V secondary by V primary, which comes out to be N secondary by N primary. So voltage ratio is directly proportional to the turns ratio. Current ratio is inversely proportional to the turns ratio. Primary by secondary, secondary by primary here. But this is when the efficiency is 100%. If loss is not there, if let us take some efficiency is given, let us take it is given the efficiency of the transformer is 80%, then you need to consider that power output will be 80% of the power input. Okay, let me write it that thing also. If eta not equal to 0, eta I am denoting for efficiency. Okay, eta is my efficiency. Let me write here, because some of the students will be just studying from the notes. Therefore I am writing also. So if eta not equals to 0, then we will say my power output will be eta times of power input. Then my V primary into I primary is equals to eta times of V secondary into I secondary. Okay, then you need to consider that. Accordingly you can find your primary and secondary. Then don't use directly the turns ratio here. Okay, use only turns ratio for efficiency 100%. This you can use generally, voltage ratio. Okay, now we are having a question on this. Let us read this question, what it is asking here. Primary coil of a transformer is connected to 220 volt AC. Primary and secondary turns of transformer are 100 and 10 respectively. So these are 100 and these are 10. If this is 220 volt, this will be 22 volt. 220 by V secondary is equals to 100 by 10. Turn ratio is getting 1 by 10. Voltage will also get 1 by 10. Secondary of the transformer is connected to two series resistance shown in the output voltage is across 7 ohm. Okay, this is 15 kilo ohm, this is 7 kilo ohm. These are resistors. So how much will be V output? We are taking 7 across 7. So some current will go, some drop across this, some drop across this, and drop will be proportional to the resistance. Okay, so if I need to write the drop here, so I'll say just 7 divided by 7 plus 22, 7 plus 15. This resistance divided by total resistance into total EMF 22. What it is? This comes out to be 7 kilovolt. Not kilovolt, sorry. Not kilovolt, because that was in volt. Everything was in volt. So 7 volt. Resistance were in kilo ohm. Anyways, that kilo unit will get cancelled here. Another question, a power transmission line feeds input power at 2300 volt to a step down transformer with its primary winding having 4000 turns. So primary turns are given as 4000. The output power at 230 volt, okay. If the current in the primary winding of the transformer is 5 ampere, the efficiency is 90%, the output current will be, okay, output current we need to find. I can say that my V primary into I primary is equals to 90% of this equals to secondary. I did mistake there. Oh, I did a mistake here. Yeah, I wrote P out both sides. That was a mistake. Let me correct it. So power output is eta times the efficiency, eta times of the power input. This was eta times of V primary into I primary. This was my V secondary into I secondary. Got that point? Okay. So V primary into I primary, eta times of this, getting it? Because output power is eta times of the input power. The same thing which I mentioned here. Again I am showing the output power is eta times of the input power. So output power is eta times of the input power, V secondary into I secondary. Now what is eta? Eta is 0.9, 90% it is, so 0.9 into what is V primary? V primary is 2300. What is I primary? Primary winding of the current in the primary winding of the transformer is 5 ampere. So this is I primary, so 5. What is V secondary? Giving the output power at 230 volts. So this is my V secondary. I secondary I need to find. Yeah. So this is 230, 10, this decimal will get cancelled, 9 into 5, 45. So I secondary comes out to be 45 ampere C. Just to do, it's a common sense, like output power will be efficiency times of the input power. This is how efficiency is defined. Efficiency is power output by power input. This is how we define. So just write output power is equals to my eta times of the input power. That's all. Now we are starting our next topic, that is electromagnetic waves. So from here, from this slide, I am starting electromagnetic waves. Let me write on the top if somebody sees the notes. EM waves. So basically the first topic that we are discussing is the displacement current. Now what was Ampere circuital law? If I ask you, in magnetism when we were discussing, you understood that Ampere circuital law was integration of B dot dl in a closed loop was equals to mu naught into I enclosed. That was the meaning. Yeah. So integration of B dot dl was equals to mu naught into I enclosed. This was my Ampere's law. Ampere's circuital law. But there was a mistake in this, and that mistake was mentioned by Maxwell. And what was that mistake? Try to understand this. So I am having a parallel plate capacitor. Here the plates which are shown are you can say circular plates. Okay. So I am having a parallel plate capacitor. This is one plate, this is another plate. One plate is having plus Q charge, another plate is having minus Q charge. Some current is moving in this. At a point on the wire, I took this point, I drew the Amperian loop, okay, circular, okay, through this, and I mentioned that integration of B dot dl here becomes my mu naught into whatever the current was passing. This current was I, so I wrote it as I. This I wrote for this. Now, if I show the Amperian loop in a different way, now I made my Amperian loop of this shape. Okay. So, I made my Amperian loop of you can say this is a closed loop. Okay. So, I made my Amperian loop of this shape. You can, how should I say? It's like a pot shape. It's like a pot shape. Pot shape means it's somewhat like this. Okay. Pot shape or a tiffin box shape. Okay. I get, now you may say, sir, it is a you can say some shape, it's not a loop. How you are saying this? No, when I am saying Amperian loop, I can choose a loop like this also. This is my loop, okay, and I am making this as my total pot shape kind of figure at the back. So whatever is the current passing through that, in that loop I can write as mu naught into I enclosed, whatever the current is passing through this part. Okay, so I can form the shape of this Amperian loop like this also. So when I say in this particular case, integration of B dot dl, this comes out to be mu naught into 0, because how much is the current that is passing? There is no current here, isn't it? Is there any current here? No, there is no current here. So it's wait a minute, how I placed my pot? No, not that way. I am saying, let me write it again. So I am putting my pot in a shape, yeah, like this. Like this, okay. So how much is the, you can say, the current that is passing through this? You may say 0. Here the current is 0, isn't it? How much is the current? You will say this current is 0. So if this current is 0, I will put 0 here. When I was making my Amperian loop like this, I will getting mu naught into I. So when I am making my Amperian loop like this in a pot kind of shape, I am getting B is equals to 0. It means there is some gap here, okay. So something is missing. We are missing something here. So Maxwell mentioned that we are missing something here. When I am writing, I am taking Amperian loop like this, I am writing it, I am getting mu naught I enclosed. When I am taking my Amperian loop like this, I am getting it to be 0. There is no, you can say, current that is passing through this. Is there any current passing through this? No, there is no current that is passing through that, that is 0. So Maxwell mentioned that there is some term that is missing in this, there is some term that you are missing in this enclosed, that is wrong, okay. So what is that term missing? He mentioned that there are two types of current. When you are saying I enclosed, you are taking only the current that is flowing through the wire, conduction current we say. So Maxwell mentioned that although between the plates there is no conduction current, but there is displacement current, okay. So he made a change to this expression and he wrote it like this: integration of B dot dl is equals to mu naught into this, my I enclosed becomes my conduction current plus my displacement current. He mentioned that this is the mistake here that we are doing. What we are doing? We are not considering the displacement current. Let me write this with different color. This is my conduction current. Let me write on the left side. This is my conduction current. and this is my displacement current. So he mentioned that we are considering conduction current means that is flowing through the wire, but we are not considering the displacement current that is flowing between the plates of the capacitor. What is that? Displacement current that is flowing between the plates of the capacitor. Now if I ask you write the flux, write the electric field between the plates, you will say electric field is equals to sigma by epsilon naught or q by a epsilon naught. Differentiate this. dE by dt. Okay, yeah, dE by dt I can do, or first let me write in different way. So I'll say let us write it like this: E into A is equals to q by epsilon naught. What E into A? That is my flux. So electric flux. Okay. So I'll say my Q comes out to be my epsilon naught into electric flux. Now differentiate this. If you differentiate it, this becomes my dq by dt. What is dq by dt? dq by dt is current. But what that current is? That is my displacement current. If you differentiate this, this becomes my dq by dt, which will become epsilon naught is constant into d phi e by dt. So this dq by dt thing, this dq by dt is my displacement current. Getting it? This is my displacement current. So we say this as my ID, that we say my displacement current. So from here I got that my this ID is basically equals to epsilon naught into d phi e by dt. Very important. Why very important? I am saying not many questions from displacement current it is asked, but if some question is asked, it will be very direct. So make sure you remember this formula. Okay, so the point is clear that in my ampere circuital law, the current that we used to consider, that was only conduction current. So we were doing a mistake. We need to consider the total current. Total current means the conduction current as well as the displacement current. And this equation, we mentioned this equation as ampere, Maxwell's ampere equation. Okay, it becomes my Ampere's Maxwell's ampere circuital law, like that. Okay, because Maxwell did the correction there. We will come to that, like I'll mention the equation there. I'm not writing here. Yeah, this is our modified ampere circuital law, or I'll say Ampere's Maxwell circuital law. Getting it? Now this capacitor is like this. Again, see one more thing. This capacitor is like this. Here your conduction current is there. In between the displacement current is there. Okay. Now if you say this conduction current was coming here, outside the displacement was 0, in between the conduction is 0, displacement is there, then it means what? Conduction current is basically equal to displacement current. Conduction current is basically equal to the displacement current. Yes, equal to the displacement current. If let us take, if you inside the capacitor, if you make a amperian loop, inside the capacitor if you make an amperian loop, and from that some part of the displacement current is passing, let us take you make an amperian loop which is having area 1/4 of the total. So how much displacement current will pass through that? 1/4 of the total. Okay. So here I will say that my this conduction current is equal to the displacement current. This topic is a bit different and a bit sometimes seems to be difficult to understand, but I explained that in a simplified way. I hope you are able to understand. Now let us do this question. An alternating voltage of amplitude 40 volt and frequency 4 kilohertz is applied directly across the capacitor of 12 microfarad. The maximum displacement current between plates of the capacitor is nearly. Okay. Alternating voltage, amplitude is given, frequency is given. Okay. Now maximum displacement current between the plates of the capacitor means what? Maximum conduction current you can find in the wire. Whatever is the maximum conduction current, same is the displacement current, isn't it? Yes. So here it is my displacement, here is my conduction current is basically equals to displacement current. So I just find the maximum value of the conduction current. Okay. So maximum value of the conduction current, IC naught, let us write, how should I write? I naught just, let us write. Okay. That will become my V naught divided by XC. What is V naught? V naught is 40. What is XC? XC is 1 by omega C. So 40 into omega C. What is omega? Omega is 2 pi F. 2 pi into F. F is 4 kilohertz into C. What is C? C is 12 microfarad. 12 microfarad. Then you can solve it. Put the values. I have already put the values. Okay, just you calculate it, mark the answer. I think approximately, yeah, nearly we need to find, because pi is there, we can put that as 3.14. Okay, make sure you put your answer in the comments. Now another question on displacement current I am showing. The displacement current of 4.425 microampere is developed in the space between the plates of parallel plate capacitor when voltage is changing at a rate of 10 to the power 6 volt per second. The area of each plate of the capacitor is this. The distance between the plates of the capacitor is this. What is the value of X? Okay. So first of all, let us write the formula for displacement current. How much is that? ID is equals to epsilon naught d phi E by dt. Can I write this in terms of electric field? I can write phi as A into A. A is constant, that will come out. Epsilon naught into A into dE by dt. What is E? E is basically potential per unit length. Okay, I can consider that I am saying that E is equals to basically minus dV by dr. dV by dr. Small r, let us use minus dV by dr. Electric field I am considering uniform only whole throughout the capacitor, that we consider. Okay, and if I write the magnitude of this, I can write this as epsilon naught into A into E, I can write as V into L. E magnitude V by L, sorry, not V into L. What is L? L is the distance between the plates. Okay, L, or let us take this as D. Generally we take D, so let us write this as D instead of L. Okay, just write D there, and now put it here. So dE by dt, so this will become 1 by D into dV by dt. Now dV by dt is 10 to the power 6 epsilon naught, we know that is 8.85 in 10 to the minus 12. D is yeah, displacement current is given to us 4.425, and what else? Area is given to us, that is 40 centimeters square. From there we can find what? We can find D, and that will come out of the form x into 10 to the minus 3. From there you can find x. Okay, got it? Put the values, everything is there. Put the values, solve it. Why I ask you to put the values and solve? I cannot do. I can do that, but when you will do, you write the formula, you put the values, this formula will be like memorized by you. Okay, so everything will go inside. Okay, so here epsilon naught is there, here A is there, here we need to write the electric field. All those things will be there in your head, and when you will go in the exam, you have the practice with you, you will see, oh, I did this. You can do quickly. Now prediction of electric field, magnetic field and electromagnetic waves. if a charge is there which is stationary, okay, a charge is there and this charge is stationary, what it will produce? Magnetic field? No. Only electric field? Yes. If the charge is stationary, it will produce only electric field. It will produce only electric field. Now, let us move this charge. The charge is q and I am moving this with speed v, which is constant. Okay, I am moving this charge with a constant speed. What will happen? What it can produce now? Tell me what it can produce now. It is moving with constant velocity. What it can produce? It can produce electric field will be there. Yes, it can produce magnetic field. Yes, current is there. Okay, magnetic field will be there. So it can produce both. My electric field will be there due to this. Okay, and it will produce magnetic field also. Okay, now if the charge is having some acceleration, it is accelerated, so what it will produce? Now here it will produce an electromagnetic wave. From the classical theory of electromagnetism, we can say a charge, an accelerating charge particle will produce electromagnetic wave. If a charged particle is accelerated, it will produce a electromagnetic wave. Now in an electromagnetic wave, we are having electric field and we are having magnetic field also. Okay, and they are oscillating. How they are oscillating, we will discuss. How, like what should say, how they are in sync with each other, that we will discuss. Getting it? So basically when we say electromagnetic wave basically combines of electric field also, magnetic field also. Okay, and they are in sync. Electromagnetic wave is there, it is traveling in a particular direction. Your electric field is oscillating, your magnetic field is oscillating. Okay, so those things will come into the discussion in a while. Now Maxwell's equations. So these are the four Maxwell's equations. You might have seen these four equations already. So this is our Gauss law. Total flux is equals to Q enclosed divided by epsilon naught. And this is Gauss law. In magnetism, we know that monopole cannot exist. Okay, only north pole or only south pole cannot exist. So any closed surface, if you take integration of B dot ds, has to be 0. This is our Faraday's law of electromagnetism that we already discussed in EMI. And last is the modified Ampere's circuital law. This we discussed today. So this combines of here conduction current and my displacement current. So this term is my displacement current, epsilon naught d phi by dt. Now basically, what are electromagnetic waves? We had a bit discussion. So an accelerating charge particle is when the charge particle oscillates about an equilibrium position, oscillating. Okay, that is also accelerated. Okay, so if the frequency of the oscillation of the charge particle is f, then it produces an electromagnetic wave of frequency f. So classical theory of electromagnetism mentions that if your frequency of oscillation of the charge particle is f, then the frequency of electromagnetic wave will also be f. Okay, yeah, so that is same. So keep this in, this is an important point. Okay, I am writing it again. So frequency of oscillation of the charge particle is same as, or I'll say equal to, my frequency of electromagnetic wave that it will produce. Okay, the electromagnetic wave that it will produce will have the same frequency as that of the oscillation of the charged particle. Now let us discuss how the electric field and the magnetic field are in sync in an electromagnetic wave. So this is a electric field and magnetic field. Here this is our direction of propagation. Electric field we are showing with let us take electric field we are showing with green color and magnetic field we are showing with blue color. Okay, now you see electric field is moving along y axis here, my magnetic field is moving along z axis here. Okay, now when the wave is propagating along the x axis, as the electric field is increasing, magnetic field is also increasing. You see, as the electric field is increasing, magnetic field is also increasing. So when it is propagating, electric field is increasing, magnetic field is increasing, and the wave is propagating in the perpendicular direction to electric field and magnetic field. You see, electric field is oscillating in a plane perpendicular to magnetic field. Electric field is oscillating in which plane here? This is my y axis, this is my x axis, this is my z axis. Electric field is oscillating in which plane? This is xy plane. Okay, so this is my xy plane. This is my electric field. Okay, magnetic field is in which plane? This is z, and that is my this is x, yeah, this is xy plane and this is xz plane. And in which direction it is propagating? It is propagating along x direction. So generally, or I'll say, I'll take that point in a while. So first you understand, when the electric field is increasing, the magnetic field is increasing. They are in phase. So if electric field is a function of some sign and some phase value is there, the same phase is of magnetic field also. When you write for magnet, the phase remains the same because they are in sync, they are in phase. So when it is increasing, magnetic field is also increasing. It is when it is decreasing, that is also decreasing. So it is moving like this. Electric field increasing, magnetic field also increasing, electric field decreasing, magnetic field decreasing, and the wave is moving in a perpendicular direction, perpendicular to both electric field and magnetic field. So the direction of propagation is basically E cross B. So this is E, my B is out of, so E cross B when I do, the thumb represents the direction of propagation. So this direction of propagation is my E cross B. This direction is E cross B. So few of the important things that you must keep in mind, two things: the phase of electric field and phase of magnetic field is same, they are in phase. Okay, they are oscillating in planes perpendicular to each other, and the direction of propagation is perpendicular to electric field and magnetic field, and that is given by E cross B. Now we are writing here our electric field and magnetic field wave equation. You know how we write the equation of a wave. So there is somewhat like kx minus omega t plus phi, like that. Okay, so with time also the amplitude is varying, with x also the amplitude is varying. So x will also be there, my time will also be there. So electric field wave equation is this: E max cos kx minus omega t plus phi, magnetic field equation cos kx. Now this, you see, this phase is same, this will remain the same. This will remain the same. And from here I can tell what is the direction of propagation. How? If this is kx minus omega t, certainly the direction of propagation is plus x axis. Here x is there, it means it is along x axis. Here minus is there, it means it is moving in the positive x direction. If it would be plus, it will be moving in the negative x direction. Where you understood these concepts? In the waves chapter. Okay, so it is here, from here I can say it is moving along plus x axis. This thing is telling me in which direction it is propagating. Here it means it is propagating in x direction, and it is a negative sign here, therefore it is propagating in a plus x direction. Getting it? If it would be kz, I will be saying it is propagating in z direction. If it would be ky, I will be saying it is propagating in y direction. Clear? Yeah. So this is my velocity, direction of velocity. And if I ask you a few of the things, let us write the wavelength. So wavelength is my lambda. Lambda is 2 pi by k, you know the formula. So 2 pi by k, what is k? This is my k. So lambda is my 2 pi by k. And if I ask you the speed v, that is my omega by k. This is my omega, this is my k. Okay. So speed of the wave is omega by k. And phi is here my some phase constant. And I can find the direction of my propagation from the direction of electric field. Let us take this is somewhat I cap, j cap will be given there, k cap or whatever it is. So from there, like what electric field is oscillating in the previous example, the electric field was oscillating in y direction, my magnetic field is oscillating in z direction. So for electric field it will be that wave equation into j cap. For magnetic field it will be that wave equation into k cap. So when you do j cap cross k cap here, okay, this is my j e, okay, cross k, that becomes my I, okay. So this becomes my I, direction of propagation. So I can find direction of propagation that way also. So two ways. One, by seeing this I can tell the direction of propagation, and by seeing the directions of this the electric field and magnetic field oscillations, I can tell the direction of propagation. Second thing is velocity is omega by k. Okay. Now electromagnetic wave is our radiations, like from the sun we are getting. What is the speed of the radiations or the light, I say? So that is 3 into 10 to the power 8. So in vacuum we know that is 3 into 10 to the power 8. So what is that basically? So in vacuum if I say, where should I write? Yeah. So speed in vacuum if I say, that is c, that is equals to 1 by root of mu naught into epsilon naught. You can put the value of mu naught and put the value of epsilon naught, and you will get that this will come out to be 3 into 10 to the power 8. Let us do that. Divide and multiply with 4 pi. Mu naught by 4 pi, and here 4 pi epsilon naught. What is mu naught by 4 pi? 10 to the power minus 7. And what is 4 pi epsilon naught? 1 by 4 pi epsilon naught is 9 into 10 to the power 9. So 4 pi epsilon naught is 1 by 9 into 10 to the power 9. So this is 1 by root of 10 to the power minus 7 into 1 by 9 into 10 to the power 9. So what it is now? This will become 3 into 10 to the power 8 meter per second. Okay, so this becomes the speed of light in vacuum. Now if let us take in place of vacuum some other medium is there, then we need to consider the permittivity and permeability of that particular medium. I'll say C, that will be root of permittivity and permeability of that particular medium. So mu into epsilon. Instead of mu naught we will take mu into epsilon, not epsilon naught. Let us write this as V now. Okay, this is for in a medium, and from here you can relate this with the refractive index also. We know that refractive index of a medium is speed of light in vacuum divided by speed of light in that particular medium. So we can take ratio and we can find the refractive index there. Now next thing, direction of propagation. We already mentioned that the direction of propagation is the direction of E cross B vector. So you see the direction of E, you see the direction of B, see the direction of E cross B, that will become the direction of propagation of my wave. Now velocity, velocity of electromagnetic wave I already discussed. Velocity is E by, one thing. Now velocity, when I was finding the velocity of electromagnetic wave, let us take this expression is given, I can find omega by k, and from there I can find the speed. Okay, or what else I can do? If I know mu and epsilon of that particular medium, or if it is space, free space, I can use mu naught and epsilon naught. From there also I can find the speed of light. in that particular medium or in vacuum, whatever it is. And also the electric field and magnetic field magnitudes are related with the speed of light in that particular medium. What is that relation? That is this relation. The ratio of amplitude of electric field and the magnetic field is equal to speed of light. Either you take the ratio of amplitudes or you take the ratio of RMS values. That is equal to the speed of light. Why, how we got this expression? Basically the energy density. Now electromagnetic wave is moving, so there is some energy in the electric field, there is some energy in the magnetic field. Okay, so whatever is the energy density of electric field, that has to be equal to the energy density of magnetic field, and from there you can get the speed of light. You want to see? Yeah, let us see. What is the energy density of electric field? So first of all, let me write energy density of electric field. This is equal to energy density of magnetic field. Energy density of magnetic field. So what is the energy density formula? In previous video when I was mentioning, I mentioned that point, the energy density of electric and magnetic field, and I told you that you must remember this. We will come back to this. So energy density of electric field was half epsilon naught E square. Energy density of magnetic field was half epsilon naught B square. So write it. So energy density of electric field half epsilon naught E square. For magnetic field, not half epsilon naught B square. For magnetic field, in place of epsilon we will use 1 by mu naught. So for magnetic field it is B square by 2 mu naught. Yeah. For magnetic field it is B square by 2 mu naught. For electric field it is half epsilon naught E square. Now when electric field and magnetic field are constant, we can use this. If what if they are varying? If they are varying, in place of E we will use RMS. In place of B we will use RMS. Okay. So from here, if the medium is having the permittivity as epsilon, then you need not consider the space, then you need to consider the permittivity of that space. Similarly, if the permeability is mu, then you consider mu, not a free space. So I am taking a general case. Let us write it like this. From here, if you write my E by B ratio, my E by B ratio comes out to be 1 by root of mu into epsilon, not epsilon naught, mu into epsilon, and this was our speed of light in that particular medium. Yes, we got. If it is in vacuum, you will get the speed of light in vacuum. If it is some particular medium, you will get the speed of light in particular medium. So basically this ratio you must keep in mind, that E by B is equals to the speed of light, or E is equals to BC. Getting? Direction of propagation is E cross B, that we already got. Now let us talk about the refractive index. Yes. So refractive index ratio, as I mentioned, it is speed of light in vacuum divided by speed of light in that particular medium. Now speed of light in vacuum, what was that? That was 1 by root of mu naught into epsilon naught. Speed of light in that particular medium was 1 by root of mu into epsilon, the permittivity and permeability there. And what is mu? Mu, I can say this is mu r into mu naught. What is E? Epsilon? Epsilon will be the relative, you can say constant, epsilon r into the epsilon, okay, naught, divided by root of mu naught into epsilon naught. Okay, so from here mu naught and epsilon naught will get cancelled, and this comes out to be root of mu r into epsilon r. Okay, let us take dielectric constant is given, which is equal to epsilon r. Okay, so that you can relate. So sometimes it is mentioned like the speed is given and the dielectric constant of a medium is asked. So all those variations are possible here. Now we are having this question. We'll come to this. Okay, let us discuss this question. What is this? A linearly polarized electromagnetic wave in vacuum is given, the expression is given to us, is incident normally on a perfectly reflecting wall at Z is equals to A, choose the correct option. Now it is reflected. When reflection happens, what will happen? When reflection happens, what will happen? The direction of propagation will become opposite. Here the direction of propagation is plus Z. It is reflected from Z is equals to A, so it will become minus Z, so here plus should be there. In whatever is my reflected wave equation, the plus should be there. If, okay, yeah, so reflected wave equation here it is mentioned, so here plus is there, that should be there. What else? One more thing that is given. What is given? It is reflected from Z is equal to, okay, that is clear to us. Now, first of all, A, the frequency of electromagnetic wave is, how we write the frequency? Now, this is my omega. Omega is equals to 2 pi f. So, 5.4 into 10 to the power 6 is my 2 pi f. So, frequency will be 5.4 divided by 2 pi. A is correct, incorrect I will say. The wavelength, what is wavelength? Lambda is equals to 2 pi by k. Lambda is equals to 2 pi by k. K is 1.8. So 2 pi divided by 1.8. So it will not be 5.4. This is incorrect. Next thing, perfectly reflecting wall it was. There is no transmission. So transmission will not be there. Reflection will be there. Direction opposite. C is correct. Okay. Another question. If electric field intensity of a uniform plane electromagnetic wave is this, okay, the magnetic intensity H of the wave is. Now here you see, here he is saying that the magnetic intensity H. He want H, he don't want B. So what is basically H and B? How we relate that? So we know that B is equals to mu into H. This relation you know. So this relation we need to use here. What else? The options are given to us. Yeah. Now, first of all, when we write the expression for H, this phase, this will remain the same. Okay, these are two separate. Okay, we need to write here. This is one equation. Okay, this is another. So two components are there. So we will write for both the components one by one. So for first component you write. This will remain the same anyway, and here also this part will remain the same. That is clear to us. Now next thing is check for the magnitudes and the direction of propagation. Here you see electric field is oscillating in x direction. Here this component is oscillating in y direction. What else? The magnetic intensity of the wave will be, the electric field intensity of a uniform plane electromagnetic wave is, okay. Now what is the direction of propagation? Plus z. So direction of propagation is plus z, direction of propagation is plus z. So what is that direction? That direction has to be E cross B. E is along x-axis. E is along x-axis. So E cross B means B should be along y. So this, when you write for magnetic, this will be AY. For magnetic I am telling, okay, so for magnetic field, okay. So this will be AY because I know that x cross y will be my z. It is propagating along plus z. So same for here, this is my y, okay. So y cross, what should be, how should I write? Y cross minus x, yeah, y cross of minus x should be my z. So here there should be minus ax cap. So for the second component it will be minus ax cap. For the first component it should be plus, here it is minus also. So minus ay. So minus ay then minus ax. So both should be negative. First thing is both should be negative. So this is incorrect, this is incorrect. Both should be negative, either C or D. Let us see now. Now we need to find the components. How we need to find the components? The magnitudes basically of both the components. So this is my E, and my, if I write my B, we know what is that, E is equals to B into C. This relation we know. So B is equals to basically E into C. So H is equals to B by mu. So E into E divided by C by mu E divided by C divided by mu naught. For free space we will take. C we know that is 3 into 10 to the power 8, and E are given. So when you write this thing, C is 3 into 10 to the power 8 and mu naught will be 4 pi into 10 to the power minus 7. So this 10 to the power minus 6 and minus 6 will not be there. C will be correct. Just by an idea I got that this 10 to the power minus 6 will not be there, because mu naught we know, and we know how much is 3 into 10 to the power 8, how much is C, that is 3 into 10 to the power 8. From there we related. Another question we are having, electric field of a plane electromagnetic wave propagating through a non-magnetic medium is given by this. Okay, the dielectric constant of that medium is equal to, so mu r is equals to 1. Now what is the speed of light? Speed of light v, that is omega by k, we know that. What is omega? This is omega, 2 into 10 to the power 10 divided by k is my this 200. So this becomes my 10 to the power 8 meter per second. Now what is the refractive index? So refractive index, when I say represent with the, let us represent this with n. Refractive index is speed of light in vacuum divided by speed of light in medium. This becomes 3. So what is this 3? 3 is equals to root of mu r into epsilon r. Mu r is given as 1, so root of epsilon r comes out to be 3. From there epsilon r comes out to be 9. Therefore the correct answer is D. Okay, so we got the correct answer, epsilon r as 9, which is our dielectric constant. Basically epsilon r is our dielectric constant. Let us begin with the next question. That is, a plane electromagnetic wave is propagating along the direction. This is our direction of propagation. This is I cap plus j cap by root 2. Okay, with its polarization along direction, that is k cap. Now what is polarization? You may not be knowing now. We will discuss this in wave optics, but I'll give you a basic idea what is polarization. So polarization means the wave is restricted to oscillate along one plane. Okay, that is the meaning of polarization. Now generally if we talk about any radiation that randomly oscillate in, let us take it like this is oscillating in YZ plane, now it is oscillating in XZ plane also, and it is oscillating in between also. So when we say we polarize this light, now we restricted this light to oscillate only along one axis or in one plane. So that is the meaning of polarization. We'll get into detail of polarization in wave optics. Okay, so here we have electric field also, we have magnetic field also. Okay, now when it says it is polarized along direction k cap, it means the electric field oscillates along k cap. Getting it? When it says that it is polarized along direction k cap, it means the electric field is restricted to oscillate along k cap, or the electric field will oscillate only along k cap. Getting it? So you'll say electric field will oscillate along my k cap. This we got from this particular line. The now next is the correct form of the magnetic field of wave would be, and these are the options. Now first of all, one thing is the direction of propagation is this. If this is the direction of propagation, inside you can say the cos or the sine function, it should be something like omega t minus of this into my k. Okay, so it means, yeah, here also we are getting, here also we are getting. It means either the expression is this, or the expression can be this, or the expression can be this. Okay, all these three expressions having negative sign here and k into that direction. Getting it? Like we used to have omega t minus kx, so it means it is going along positive x direction. Now minus k into this direction, it means it is going along positive of this direction if negative sign is there. Okay, so that we got, that is there in three options now. But now we need to know what is the direction of my magnetic field oscillation, that I need to know. Now come here, let us draw my x-axis and y-axis. That will give you a idea of the directions. Now this is my x-axis, this is my y-axis, and out of the plane I am considering my z-axis. Now here the again I am saying that this is the direction of propagation. It means the wave is moving in this direction. Okay, this is the direction of propagation of the wave, and this direction is my I cap plus j cap by root 2. It is going at an angle 45 degree. It is moving in this direction. Electric field is oscillating along k cap out of the plane. Electric field is out of the plane along k cap. Where the magnetic field will be? Certainly we know magnetic field will be oscillating in a plane perpendicular to the direction of the electric field, that we know. That is clear. And also we know that E cross B should be the direction of propagation of the wave. Wave is propagating in this direction, electric field is out of the plane. So if I do E, out of the plane, E cross B, the magnetic field should oscillate in this direction. You see, E is out of the plane, E cross B if I do, E cross B if I do, then we are getting this direction. That is the direction of propagation of the wave. It means the magnetic field should oscillate in a direction minus of I cap plus j cap by root 2. This direction, here this angle should be 45 degree, okay, and it is in along this direction. What is this direction? This is here I is positive. Yeah, I did a mistake here. Let me check again. So that is E, and cross B, E cross B is in that direction. This is not I cap plus j cap. Here my j is negative, I is positive. Because if we move in this direction, what is? My x is positive, my y is negative. So this is I cap minus j cap by root 2. Perfect. I cap minus j cap by root 2. Now come to the options. I cap minus j cap by root 2. You see, here this is I cap plus j cap, that is incorrect. And this is k cap. K cap is the direction of oscillation of electric field, not of the magnetic field. So C is correct. So again I am repeating, the concept that is important to understand is how to find the direction of propagation of the wave from the expression. One thing is this. Next thing is that E cross B is the direction of propagation of the wave. If I know the oscillation direction of E, I can find the direction of oscillation of B. Okay, fine. Now let us talk about the energy density associated. As I already mentioned, we know what is the energy density due to electric field, what is the formula of energy density due to magnetic field, and we have derived these formulas when we discussed about electric field and magnetic field. So the energy density of electric field was half epsilon naught E square, energy density of magnetic field was half epsilon naught B square. Okay, so let me write it again. It is very important. So energy density of electric field what is that? Half epsilon naught E square, and energy density of magnetic field is B square by 2 mu naught. Sometimes by mistake I mention half epsilon naught B square. No, there is not epsilon naught there, we need to consider mu naught, and that is 1 by mu naught. So B square by 2 mu naught, okay. If I mentioned that wrong, I am again correcting it. That is B square by 2 mu naught. So energy density of magnetic field is B square by 2 mu naught. Now the point is, here electric field is varying, it's not constant. Magnetic field is varying, it's not constant, it is oscillating sinusoidally. So which value of E you will consider? Should you consider the peak value or which value? No. Here if it is oscillating sinusoidally, here we will consider the RMS values. RMS I already mentioned how to find that. So here it will be RMS. It will be RMS. Okay. And again I am saying here that RMS value is peak by root 2. Similarly, RMS value of magnetic field is B naught by root 2. Okay. Now, one important thing that I already mentioned before some time, that was that the energy is equally divided between the electric field and the magnetic field. Total energy is there E. So, half of that is in the electric field, half of that is in the magnetic field. Okay. So, total, if I say total energy density, that will be energy density due to electric field. How much? Half epsilon naught ERMS square plus the energy density due to magnetic field, that is half BRMS square divided by mu naught. And I mentioned that these two are equal. So, half epsilon naught ERMS square is basically equal to BRMS square divided by 2 mu naught. Energy is equally divided among electric field and magnetic field. 50% is with the electric field, 50% is with the magnetic field. Okay. Now I can write this as twice of 1. Yeah, I can write it as twice of 1. So I can write this as twice of half epsilon naught ERMS square, or I can write it as twice of BRMS square divided by 2 mu naught. I can write it like this. Yeah, and I know that ERMS is equals to E naught by root 2. So if I write this as E naught by root 2 square, so this 2 will get cancelled. So this will become half epsilon naught E naught square, and which is same as half epsilon naught not epsilon naught. This is B naught square by 2 mu naught. So you may remember this in terms of epsilon naught, or you may remember this in terms of E naught, or in terms of RMS also. Sometimes it is mentioned that in the question that this is the total energy density. If this is the total energy density, I can equate it with half epsilon naught E naught square or B naught square by 2 mu naught. If sometimes it is mentioned that the energy associated with the energy density due to electric field is this, then that is half of this, or you can write it in RMS form. Okay. Now let us read this question. In a plane EM wave, the electric field associates sinusoidally at a frequency of 5 into 10 to the power 10 hertz and an amplitude of 50 volt per meter. The total average energy density of electromagnetic field of the wave is. Okay, total energy density we need to find. Total energy density means half epsilon naught E naught square. Okay, now here the amplitude of electric field is given. Therefore, I wrote this formula in terms of electric field. If it would be magnetic field, I would have mentioned in terms of magnetic field also. Okay, so this we know. Now let us put the values. So half epsilon naught is 8.85 into 10 to the power minus 12. And what is amplitude? Amplitude is 50 volt per meter. So 50 square. Now you can solve it and mention your answer. Now you may ask, sir, it is independent of the frequency. Yes, it's not depending on the frequency. The energy density depends upon the amplitude, not on the frequency. Clear? Make sure you mention your answer in the comments. Now let us discuss about intensity of electromagnetic wave. What is basically intensity? How we define intensity? We say intensity is energy per unit area per unit time. Okay, so let us take electromagnetic wave is propagating in a direction. Okay, I have a lamp like here And so, okay, so the lamp is switched on, the light is going like this, electromagnetic wave is propagating in this direction. So you take a cross section that is perpendicular to this electromagnetic wave. So from that cross section you see how much energy is passing per unit area per unit time, that will become the intensity of this lamp. Okay, so we say, let us take, my radiation is going in this direction. Okay, I'll take a cross section like this, which is perpendicular to the direction of propagation. From this cross section I'll say how much is the energy per unit area, or first let me write it as energy per unit time per unit area. Okay, so this will become my intensity. Now if you say energy per unit time, what is that? That is power. Energy per unit time is power divided by area. So we write it like this also, that my intensity is basically power divided by area. Okay, intensity is my power divided by area. Or let me write this expression for intensity in terms of electric field. So let us take radiation is passing through this cross section. Okay, in an interval delta t, the distance traveled by the radiation is, let me write from here to here, is, let us take delta x in interval delta t. So how much energy that passed? I'll say the energy that passed, and also here the cross section of this beam I am considering as A. Cross section area is A. Let me write with a different color. So here I am considering A as my area of cross section. Cross section. Okay, now tell me how much energy has passed, total energy. So I'll say that is energy density, my energy density into the total volume. How much is the energy density? Half epsilon naught E naught square. This is the energy density into delta x, okay, into area. This becomes the total energy. Now total energy per unit area, per unit area, per unit time, per unit time. This becomes my intensity. Okay, now A is getting cancelled. What is delta x by delta t? That is the speed of the radiation. What is the speed of the radiation? I am considering by default that my radiation is going in free space. Okay, it's traveling in the free space. So what will be the speed? Speed of light, c. So this becomes intensity formula, that is half epsilon naught E naught square into c. Okay. Now, if you individually talk about how much is the intensity due to electric field, how much is the intensity due to magnetic field, so half due to electric field, half due to magnetic field, 50-50. Okay, so if only due to electric field, I'll write here RMS. So 1/2 factor will be considered there. Only due to magnetic field, if I write, I'll say this will become BRMS square by 2 mu naught into C. Okay, so it is basically the sum of the two. So what is that? Half epsilon naught ERMS square into C plus BRMS square by 2 mu naught into C. Okay, the sum of the two, each term is equal, so it will become like this, as we already mentioned that. So sometimes this thing means this thing gives us confusion. So sometimes in the question the let us take peak value is given. Sometimes they are saying, talking about the total intensity, sometimes they are talking about the intensity due to only electric field or intensity due to only magnetic field, then you need to consider the formula accordingly. Now let us discuss this question. Intensity of sunlight is observed as this at a point in free space. What will be the peak value of magnetic field? Now he is asking about the peak value of magnetic field. So write the formula of intensity in terms of magnetic field. What it will be? What it will be? We wrote this formula like this, half epsilon naught E naught square into C. Can you write this formula in terms of magnetic field also? Yes, it will become what? B naught square by 2 mu naught into C. It's the same thing. This becomes in terms of the peak value of the magnetic field. Now write it here. So this is B naught square by 2 mu naught into C. This is my intensity and this is given as 0.092. Now see the unit of intensity. This is watt per meter square. Watt is power. Power per meter square. Power by area. Okay. So the unit is correct. SI. Okay. Now what else? What we need to find? We need to find B naught. You can put C as 3 into 10 to the power 8. You know mu naught, that is 4 pi into 10 to the power minus 7. From there you can get the value of mu naught and you can put your answer in the comments. Make sure you do that. Another question we are having. Let us read it out. Suppose that I mentioned it properly. Yeah. Suppose that intensity of a laser is this. The RMS electric field in units associated with this source is close to the nearest integer is RMS value of electric field. So write the formula in terms of electric field. I'll say so this is half epsilon naught E naught square into C. This is my intensity. From here I'll write my E naught first. What is that? This is 2I by epsilon naught into C and root of this. This becomes my E naught. E naught is the peak value. It is asking for the RMS value. So that will become E naught by root 2. So E RMS is equals to E naught divided by root 2. And if you do it, it will become root of I by epsilon naught into C. What is I? I is 315 by pi. What is epsilon naught? 8.86. into 10 to the power minus 12. What is C? C is 3 into 10 to the power 8. Now you can solve it and then you can approximate the answer to the nearest closest integer. Okay. So let us take in closest integer. The answer comes out like somewhat maybe 5.8. So then you need to write 6 there. Okay. So whenever the question is like this, approximate to the approximate closest integer. So find your numerical value up to at least 1 decimal places. Up to at least 1 decimal places. Let us take you did calculations and you got the first number as 5. So you thought, okay, nearest integer, I'll write 5. No. If it is 5.8 or 5.9, then you need to write 6 there, isn't it? Yeah. Now radiation pressure. As we know, radiation has energy. We already discussed. Radiation has momentum. Yes. So radiation, if radiation is having energy, having momentum, so it will have some pressure also due to that. Okay. Let us take radiation falls on a surface. It means if energy is there, momentum is there, some pressure will be applied on the surface there, isn't it? Yes, there will be some force due to that. So radiation pressure is basically, I'll say, the force per unit area by the radiation. Force per unit area by the radiation. When we say pressure, we say force per unit area, isn't it? Now, so when I say radiation pressure, I'll say it is force per unit area of the radiation. Okay. So, or in simple words, I'll just write this is pressure due to the radiation. Now you may say, sir, but the radiation is falling from the sun. We are not feeling that pressure. Yes, you are not feeling that pressure because that value is very, very less. That value is very, very, very less. Therefore, we are not feeling that pressure that there is some light that is falling on us. Okay. Otherwise pressure is there. If energy is coming, momentum is there, some force will be there, okay, some pressure due to the radiation will be there. Now let us do a derivation. In general derivation, let us take a radiation is falling at a particular angle theta with the vertical on a surface, okay, and here this area of the surface is A. Now let us find how much will be the pressure on this surface due to the radiation. Then we'll generalize the result for theta is equals to 0, for perfect reflection, for perfect absorption, all these things. Now radiation is falling, it may be perfectly absorbed, it may be perfectly reflected. Take an example like a ball, okay, let us take a ball is there. A ball strikes the surface and then let us take this angle is theta and let us take the collision is perfectly elastic. After striking the surface, the ball is going in this direction with the same speed. It was coming with u, it is going at an angle theta with u. Now how much is the change in momentum of the ball? You will say momentum is only changing in the horizontal direction. In the vertical direction there is no change in the momentum. In the horizontal direction the momentum is changing, and that is 2 mv cos theta, okay, isn't it? Initially the horizontal momentum was in this direction, how much? That was mu cos theta. And finally the horizontal momentum is in this direction, what is that? That is mu cos theta. The change in momentum is 2 mu cos theta. From there we may find the force corresponding or the pressure, like that. So same thing we will do for this beam also. Here this beam is falling, okay, and this beam is falling through this is the area, and the area of the surface is given to us A, and the angle with the vertical of the beam is given to us as theta. First of all, let us try to understand how to write the momentum due to a particular radiation, okay. Now in modern physics you will understand what is the momentum due to a photon. Due to photon we write the momentum of photon as h by lambda, and if I multiply and divide with c, hc by lambda basically is the energy, okay. So this becomes like my energy that I may denote with E divided by c. So this becomes my momentum basically. So here when I say momentum due to this radiation, I'll write this momentum as the energy of the radiation, we are denoting that with capital U, okay. Energy density we denote with small u, energy we denote with capital U. So that is capital U divided by c, energy divided by the speed of the light, that is the momentum. Now this momentum is in this direction P. After reflection the beam will go in this direction at an angle theta. I am considering perfect reflection, means total radiation is reflected, okay. I am considering the example for perfect reflection. Perfect reflection or full reflection. Perfect means it is fully reflected. So this was P. Now P is in this direction. How much is the change? The change is only in the which direction? Vertical direction. So how much is the change? Vertically it was P cos theta like this. Finally it is in this direction, that is P cos theta. So total change in momentum if I talk about, that is 2 m into not mass. This is 2 into P into cos of theta. This is the change in momentum. Now what I need pressure. I need to find pressure. So first of all let us find force. Force is del P divided by del T, okay. This is my force, change in momentum per unit time, yeah, okay. And if I divide this with my area, which area? This area A, this will become my pressure, isn't it? Yes, okay. Now let us write further. Okay, so let me write P as U by C. So this is 2 cos theta divided by A into delta T into P. P is energy divided by speed of light. Speed of light is c. And what is U? U is energy. So energy, total energy. How will I write this as? My energy density, okay, into area into delta T. Yeah. So this is energy density. Energy density is half. Let me write it, that in terms of. Okay, first of all, let us write this as U by C only, because I'll directly write that in terms of intensity. I'll not write in terms of epsilon naught and my E naught square like that. Okay. Now from here, what we can simplify? I know energy density, my intensity is energy per unit area per unit time. So if I say here intensity is I, here intensity is I. So what is I? I is energy per unit area. What is this area? Area of the cross section. What is this area? This is A. So this will be, here you see, with the vertical the angle is theta. Okay. So with the vertical the angle is theta. If this is A, this will be A cos of theta. So this is my A cos of theta. Yeah. Yeah. So this, if you see, this area will have two components, this and this. So I am taking this component, that becomes my A into cos of theta. A into cos of theta. That particular angle is theta. Okay. So this is my A. This becomes A cos of theta. So divide, this is my intensity. Intensity is U by A cos of theta. Okay. So U was energy per unit area per unit time also. So per unit time. This becomes my intensity. Now here U by A delta T I have, let us multiply with cos theta also here. So if I multiply with cos theta here and divide also, like in numerator also, it will become cos square theta there. Now this term becomes my intensity. Yeah. So this becomes my 2I by C cos square theta. This becomes my pressure. Oh, let me write it, pressure itself. And this is for perfect reflection. Okay. So this is for perfect reflection. If the perfect reflection is not there, if perfect absorption is there, okay, so perfect absorption is there, then it will not be twice of that, then it will become just I by C cos square theta. Okay. So if I write for perfect absorption, so my pressure will be I by C cos square theta. And here also you can write, like if theta is 0, for theta is equals to 0, pressure will become 2I by C. Okay. Here if theta is 0, this pressure will become just I by C. Now sometimes it is mentioned that a fraction of that is perfectly reflected, a fraction of that is perfectly absorbed. Okay. But let us take 50% is perfectly reflected and 50% is absorbed, or some other ratio like 0.4 of the fraction. Okay. So 0.4 of the total is perfectly reflected and other is absorbed. If it is like that, then you may write it like, okay, so if fraction, let us take R is perfectly reflected. Okay, so I'll say the pressure will become 2I by C into R cos square theta. Okay, R portion is perfectly reflected, other 1 minus R will be absorbed. So I by C into cos square theta into 1 minus R. This becomes my total pressure. Don't remember this formula? For mains, remember these. Okay, fully, like that is for some fraction is reflected, that is not generally asked in mains, that is not asked. But if you want to understand that, it's not that difficult to understand. Just R times of due to the perfect reflection, 1 minus R due to the perfect absorption. Okay, and if it is generally, if we say it will say like it is fully reflected and it is fully absorbed, then you use this formula. And most of the times theta will be 0. Like in the question they will be given the condition such that the theta is 0. Then you just use 2I by C, here I by C. Now let us see some of the questions on this. A point source of light is placed at the center of curvature of a hemispherical surface. Okay, the source emits a power of 24 watt. The radius of curvature of the hemisphere is given. This is my radius R. The inner surface is completely reflecting. Okay, completely reflecting. Okay, the force on the hemisphere due to light is. This is my hemisphere. My point source is here. Okay. Now, if you see, all the points on the hemisphere are at equal distance, that is equal to R from this point source. It means intensity at all the points is same. And how much is the intensity? Power divided by this energy is distributed in complete sphere 4 pi R square. This is my intensity. Now, if I take a ring here, let us take this ring. On this ring, this radiation will be falling. Okay, so how the radiation will be falling? It will be falling like this. It will be falling like this on this ring. Now, on this ring, you may say the force will be, let us take, this is my circular ring. The resultant force that will be in the vertical direction, isn't it? On this ring, the resultant force will be in the vertical direction, because if you consider any part, so the force is, let us take in this somewhat like this. So what will happen? Some part will be vertical, some component will be vertical, some component will be horizontal. All the horizontal components will be cancelled from symmetricity, I can say. Only the resultant force on this ring will be in the vertical direction, isn't it? Yeah. So if I write only the vertical component dF, okay, only the vertical component I am writing. Wait a minute. I am considering with the vertical, this angle as theta, okay. This is with the vertical, okay. So when you will write the vertical component, okay, that will become my dF into cos of theta. What is my dF? dF is the intensity I by C. Okay, it is falling at an what angle? What is the angle between area and this the light that is falling? 0 degree, because it is falling perpendicularly on the surface. Okay, so I'll just write I by C, because here there the light is falling perpendicularly and it is perfectly reflecting. So 2I by C, this is the pressure into the area. Here area is, let us take dA, area of this ring. So this becomes my dF, and I'll put this dF here. So this will become my 2I by C into cos theta into dA. That is the vertical force on this ring. I need to integrate this theta from 0 to I can say for this hemisphere I need to find, so I'll integrate. But wait a minute, if I write it here, this is my dfy, what is that? 2I by c cos theta into dA. So what is dA basically here? Area of this ring. How much is the area of this ring? 2 pi. The radius of this ring is r cos theta. So dA is equals to 2 pi r. Okay. So wait, why I am saying wait a minute is, I can simplify this in two ways. Either I can say this is the projected area, that I can just directly write dA cos theta as pi r square. This is the projected area actually. But I can mathematically also simplify that. How? What is my dA? dA is 2 pi r cos of theta. Wait a minute. This is r cos theta, this is r sin theta. 2 pi r into sine of theta, yeah, into the thickness, okay, that is rd theta. Two pi r sin theta into the thickness of this ring, that is rd theta, and then you can write dA there and then you can simplify. But what I can say directly is, as I am taking only the horizontal component, okay, that is only the vertical component, okay, that is my here 2I by c cos theta into dA. Here this is my variable dA cos theta, okay. So when I integrate it, this dA cos theta will give us only the projected area. Now let us take how much is the projected area. This is my hemisphere. How much is the projected area that will be here in the vertical direction? That will be just the flat surface, pi r square. It's like the light is falling like this, it's a hemisphere, it will be circle that will be drawn at the bottom. So that is just pi r square. So you can just directly also say this is 2I by c into pi r square, if you can visualize it. Otherwise you can write dA there and you can simplify that way also. Now what is 2I by c? So 2 into intensity is power by area, okay. So 2 power divided by c into area is 4 pi r square into pi r square here, okay. So intensity I wrote as p by 4 pi r square. This pi r square is getting cancelled, so this becomes p by 2 into c. What is p? P is 24 by 2 into c. C is 3 into 10 to the power 8, okay. This becomes 6 into 4, yeah. So this is 4 into 10 to the power minus 8. So this becomes 4 into 10 to the power minus 8 Newton. This was a very difficult question, one of the difficult question I'll say in mains, and I took it so that I can take some of the difficult question as well, so that you just try to visualize it, how it is happening. Okay, this was a bit difficult question. If you are having difficulty in understanding it, it's okay, but try to understand it. Is now here the most important part is taking the projected area. If you do that, this is just quick. 2I by c into dA cos theta. dA cos theta will give us the projected area, that is my pi r square. Just put pi r square, everything is simplified very easily. Now let us talk about electromagnetic spectrum. In electromagnetic spectrum, we have different frequency or different wavelengths, and we categorize them. Like the light, that is radiation that is falling from the sun, it is having all different varieties of wavelengths or frequency, anything we can say. When a light is passing in a particular medium, the speed of the light is constant, okay. So when the light is coming from sun to earth, okay, the light is traveling in vacuum, the speed of light is 3 into 10 to the power 8. Whether whatever may be the frequency, whatever may be the wavelength, the speed of the light will be 3 into 10 to the power 8. So there, even you consider gamma rays or X-ray, they will be traveling with the same speed. Their wavelengths will be different, okay. The relation between speed, wavelength and the frequency is C is equals to F lambda. This is the relation. So when it is coming from a particular medium, this is by constant. Okay, frequency changes mean wavelength changes. Greater the frequency, lesser will be the wavelength. Lesser the frequency, greater will be the wavelength. Okay, so the light is coming from the sun. All the rays that are coming, they are coming with the same speed, that is 3 into 10 to the power 8, but their wavelengths are different. And we have categorized this entire spectrum in different parts. Okay, so we mentioned that this part will say this part will say this part will name this. Okay, different names are there. So this whole spectrum is categorized into these parts. Okay, one is the radio. After radio, the microwave is there. Okay, after microwave, infrared is there. After infra, visible is there. After visible, ultraviolet is there. Then X-ray is there. Then gamma is there. And this, when we are moving from this to this region, when we are moving from radio to my gamma, the energy of the radiations is increasing. The frequency is increasing. Means when the frequency is increasing means the wavelength is decreasing. Getting it? So when I go from radio to gamma, my frequency is increasing. Gamma rays are having high energy. X-rays are having high energies. My radio waves are having very less energy. Okay, and the wavelength of the radio waves is greater. The wavelength of the gamma rays is lesser. Lesser the wavelength, greater the energy. Try to understand it. Lesser the wavelength, greater the energy. Means greater the frequency. Generally, how we write the energy of a photon? H into F. Planck's constant into the frequency. This is how we write the energy. So greater the frequency means greater will be the energy. Getting it? So the categorization is made like this. Okay, so first we have radio, then we have here microwave. Okay, then infra, then we have visible, then ultraviolet. Okay, then we are having X-rays, then we have gamma rays. Now let us talk about each of them one by one. So first of all, let us talk about the radio waves. We are starting from the right hand here, right of me, lesser energies first. So how radio waves are produced? So these are produced by accelerated charges in conducting antennas. Now when we are talking all these about each of the radiation, which things need to be kept in mind? If you see, when we are talking about each of the radiations, the important things that should be in your mind is how they are generated, produced. Okay, a rough estimate of their wavelength. If you cannot memorize the rough estimate of the wavelength, at least try to memorize the sequence. Radio is at highest wavelength, then this comes, then this comes, then this comes, then this comes. At least the sequence should be there, because in multiple choice questions many times on one side the wavelength is given, on other side the names are given. Now match it. Okay, so that is must. So a rough estimate of wavelength is needed, or at least the order of the wavelength, or I can say the sequence of the wavelength, which is having higher wavelength, which is having lesser wavelength, that should be clear to you. Next is the application part. This is very important. This is very important and this is very important. Production is not so much asked. Production is not asked. But if you can memorize, that is good. But application is very important, and rough estimate of range, not exactly. So in application also many times the questions are like this. On one side some applications will be given, on other side the names will be given. Now you need to match. Okay, which application is for X-ray, which application is for gamma rays, which application is for microwave, like that. These type of questions are many times asked in mains. In 2024 also these questions were asked, such questions were asked. Okay, so for radio waves the application is radio broadcasting, television transmission, mobile communication, wireless communications. Next is our microwave, and you know this is the wavelength range. Then the application, if we talk about microwave ovens, we have the radar systems. This is important to remember. Next is the satellite communication. Next is the Wi-Fi and mobile network. Now you need not go into much detail. Okay, need not go into much detail how the radar system exactly work. No, that is not needed for us to understand. What we need to understand, that microwave is used in radar system, that only. Therefore I am not explaining the points here, I am just showing you. So you may take screenshots here, or like you will get notes directly also. So from there also you can access this. So here we have, this is the wavelength range, and application we have remote controls, we have then thermal imaging, night vision devices, physiotherapy. Now infrared rays are generally called as the heat rays also. Okay, so in thermal imaging, like the cameras which can sense the thermal, okay, the thermal imaging means where the energy is there. So if somebody is walking, let us take everywhere is ice, and you have that camera, and from there you can easily sense, okay, where a person is walking. Okay, if there is somebody or some heat source is there, so you can sense with help of that. So we also call thermal infrared rays as thermal rays. Okay, and also these are responsible in greenhouse effects also. Like in greenhouse effect we have CO2 and water vapors, all these that are there in the atmosphere. So what happens, the radiations from the sun are falling on the surface of the earth becomes very hot, okay, at higher temperature. So at higher temperature it will radiate infrared rays. Okay, now these infrared are radiated, these are captured by all these gases, okay, greenhouse effect gases, okay, and then they increase the temperature. So we say that infrared rays are also responsible for the greenhouse effect. And remember all these points. Next is the visible light, and for visible need not explain anything, you already know. Next is the ultraviolet. Here if we see the applications, yeah, for sterilization we use it, yes, for detection of fogged currency notes, okay, vitamin D production, fluorescence, okay, at least this you should remember. Here application of X-rays, we have medical imaging, we know that, like we use X-ray for there is a fracture in the hand is there, okay, then we detect that with the help of X-ray. Okay, security scanning and crystal structure analysis, this point is important, crystal structure analysis. Next, the gamma rays, and these are of having the highest energy. Gamma rays are having the highest energy, and we use this for cancer treatment, yeah, sterilization of medical equipment, yeah, and nuclear research, all these things. Protection is also given, you can just read it. Now let us see some of the type of the questions that are asked from here. You see, one type is this, the range is given, and here you have different names of the electromagnetic waves. Now at least when I say, at least try to remember the order which is having the highest energy. So here if I say gamma rays are having the highest energy, okay, gamma rays are having the highest energy. Highest energy means least wavelength. Which one is the least wavelength? Which one is the least wavelength? First one is the least wavelength, less than 10 to the power minus 3. So I will say for D I am having 1. Next is X-rays, okay. Now which is the next least after this? After this I will say this is the fourth one which is next least, isn't it? Yeah, 1 mm to 10 to the power minus 3 mm nm, okay, yeah, so fourth. Next we are having ultraviolet. So for ultraviolet, now we had this and we had this. From these two, which one is the least? This is from 400 to 1 nanometer, okay, and this is from 1 mm to 700 nanometer. So this is the least, second is the least. So for B we will have 2, okay, yeah. Then what? Then we are having infrared. Infrared, the last one, that is 3. Is this clear? If you just memorize the sequence, that is also enough to like match. You may not remember exactly what is the frequency of the gamma ray or what is the frequency of X-ray here, but we can see here. First of all, gamma ray is having the highest energy, so I took the least one. So what was the least one? 10 to the power minus 3, less than. Then X-ray, next highest, next higher, next least is this. Then ultraviolet, then ultraviolet was having, now these two were remaining. From these two, which one is the least? This is from 1 mm to 700, and this is from 400 to 1 nanometer, okay, 400 nanometer to 1 nanometer, okay, 400 nanometer, and everything is fine, yeah. So from here we got that the next least is my second one, okay, and the last one remaining was the third one. So I got 3, 2, 4 and 1. 3, 2, 4 and 1, that is my option B. Okay, yeah. Now another type of question is this. Here some applications are mentioned and here the names of the electromagnetic waves are given. Now here you need to memorize all the applications. As I mentioned, applications are very important to memorize. So ultraviolet rays, what was the use of ultraviolet rays? Sterilizing surgical instruments, yes. Then microwaves for no, microwaves are for radar system, yeah. Radar system we use microwaves. Then we have infrared, that is responsible for greenhouse effect. And then we are having X-rays, that is used for study of the crystals. So we are having R, S, Q and P. So R, S, Q and P, option A. Getting it? And the last part of this section was like there you need to memorize things. You need not go into much detail. You need not go how the radar system is working, how we study the crystals using X-rays. That is not on our level. That is not needed for us. Just try to memorize the applications, try to memorize the sequence, all those things. Okay. So this is all about these two particular topics. We have went into great detail of each of the subtopic. We saw different varieties of the question, whatever till now is asked by NTA. There were some difficult questions also which I took. There were very easy questions also which I considered here, so that you can see there are, if the difficulty is very high, so up to this level we can go. If the difficulty is not that high, very easy questions are there, it will be of these types. So you have that idea. Now what is needed from your side is that if you completed this video, make sure you comment completed, and as I asked for answers also in between, so you can mention your answers also of different questions. After that you need to practice questions. For that, what you need to do, in the description we have the link of our batch. Okay, you click that link, you'll go to the PW app, there is our free batch. From there you can access these notes, whatever I have written, you'll get that. With that, the practice sheet, okay, so that you have a parallel practice also on these questions. Okay, so that's all from my side. Thank you all, have a nice day.